Welcome to Advanced Haskell Data Analysis from Pact Publishing. My name is James Church. In this video series, we will cover advanced data analysis techniques in the language of Haskell. In our first section, we will cover the basics to data analysis. We'll cover topics such as computing simple statistics, connecting to a database, and plotting a chart. In section 2, we will cover linear regression. The dataset that we will be looking at is the census data of the United States, and we'll be trying to answer the question is if there is a relationship between the year and the population. In section 3, we will study multiple regression, and we'll be looking at the movie lens dataset. We'll be trying to answer the question is if there is a relationship between the genre of a movie and how that movie is rated. Now, because a movie can be associated with multiple genres, you can see how this problem will get complicated very quickly. In section 4, we'll be studying text analysis algorithm. Our dataset will be the Federalist Papers. We will be studying author similarity and an algorithm known as TF-IDF. In section 5, we will be studying the structure of data using clustering algorithms. The two algorithms which we will be covering are known as the k-means clustering algorithm and the hierarchical clustering algorithm. In section 6, we will look at the problem known as Naïve Bayesian Classification. We will be looking at the Enron email dataset, and we'll be trying to create our own spam detection algorithm. In section 7, we will be covering principal component analysis, and our dataset will be the movie lens dataset. We will be creating a movie recommendation engine using principal component analysis by studying the eigenvalues and eigenvectors of a large dataset and using dimensionality reduction to compress that dataset, so to speak, into a smaller dataset that can still be used for recommendations. Thank you for joining me, and I hope you enjoy the video series.
So section 1 is brushing up on the basics of data analysis. In this section, it's going to be the topics of converting CSV files to SQLite 3 files. The reason why we focus on SQLite 3 as opposed to CSV is because SQLite 3 files are more versatile in data analysis than CSV files, especially in Haskell. CSV files tend to be a bit cumbersome. We're going to be understanding the basics of regular expressions. We're going to be visualizing a dataset using the EasyPlot library, and we're going to be performing kernel density estimation on a dataset. So this video 1.2 will be looking at converting a dataset into SQLite 3. And this is something that I'll be expecting you to do as a student of this series for videos in this course. So once you learn how to do it, I'll present a dataset at the beginning of a series and then say, please convert this dataset to SQLite 3, and hopefully you'll follow these steps and polish your datasets. So in this video, we're going to take a look at finding a dataset online. We're going to be cleaning that dataset, and we're going to create a database based on that dataset in SQLite 3. So let's go over to our virtual machine. So I'm back in my Linux virtual machine. I'm running a net install of the Debian kernel, iHaskell installed, and I have the Jupyter Notebook system installed, and I have several libraries, including the SQLite 3 package installed. And what we're going to do is we're going to find a dataset and convert it to SQLite 3. So I've done a search in my browser for Old Faithful Dataset CSV, and I have found a dataset on Carnegie Mellon University's website. It is from 1991 titled Old Faithful Geyser Data. And there are two columns to this data. We have two variables, 272 observations of the Old Faithful Geyser in Yellowstone National Park, Wyoming. And what we have are the eruption time in minutes for Old Faithful and the wait time between eruptions. And what I would like to do is convert this dataset into SQLite 3. So I'm going to start at the 1 here, and I'm just going to grab everything. I'm going to scroll all the way down to get all 272 rows. I'm going to copy that. I'm going to swap over to my terminal. And right now I'm in my data folder of my iHaskell environment. So what I like to do is I like to keep my notebooks in one folder and my data sets in a separate folder. And you see that we have several data sets from our previous video series. We're going to be picking up where we left off and using that same environment. So let's create our data set. So I'm going to call this oldfaithful.csv. And I am going to paste the data into my data set. Let's scroll back up to the top. So you'll notice that we have several spaces between each of the columns. And what I would like to do is to convert those spaces into a single comma. And there is a command in VI to do just that for us. So every row in our file, we are going to do space star, and we are going to replace that with a comma. And if it occurs multiple times on a line, and in this particular file it happens twice per line, we are going to make this change. So there's the command, $s/space star /comma/g. Whenever we run that, we see that there were 544 substitutions on 272 lines. I'm going to go back up to the top of my file, and all of my spaces have been converted to a single comma. Great, my CSV file is ready. I can convert this to a SQLite 3 database. Now, if you'll have SQLite 3 ready, we will create the old faithful SQLite 3 dataset. And now we're at the SQLite 3 command line. We need to create a table. So let's create the Old Faithful table. So this will be the Old Faithful table in the Old Faithful database. There is an ID column, which is an integer column. There is an eruption column, which is real data. And then we have a minutes column, which is integer. Great. Because our file is a CSV file, we need to change the input mode to CSV. So that's .mode CSV. And then we have to do an import. So we import the Old Faithful file.csv into the Old Faithful table. And at that point, our database should be populated with data. And there's one way we can check on this. We can do a select query. So I'm going to select everything from Old Faithful. I'll just say limit 4 to get the first 4 records. And we see the first 4 records in our file. At that point, we're done, and I can hit Control D, and I am out of my environment. So there we go. This video covered how to create a data set, how to clean that data set, and convert that data set into a SQLite 3 file. So our next video is going to be on the basics of regular expressions in Haskell. This video will cover regular expressions. So regular expressions are a way of validating text based on a pattern. So in this video, we're going to take a look at importing the regular expression library into Haskell. We're going to be exploring some of the features of regular expressions very quickly in this video, and we're going to be applying those regular expressions to a corpus of text. Regular expressions are fundamentally about atoms. Now, atoms are any single character. Atoms can be grouped together into sequences of characters using parentheses. So A is an atom, but ABC is not an atom until it's been grouped together with parentheses. And the dot is a special atom in regular expressions which matches any single character. Atoms can be further modified using the repetition modifiers. And there are 4 repetition modifiers which you should be familiar with. All repetition modifiers work on the concept of a range. In other words, the minimum and maximum number of characters which are matched in order to say that an atom validates a pattern. So the first modifier is the question mark, and it works on the range of 0 to 1. An atom can appear 0 times or it can appear 1 time. It's the optional modifier. There is the asterisk, which works on the range of 0 to unlimited. So a range modified with The asterisk can appear 0 times, or it can appear as many times as we need. If we want something to appear at least once, or any number of times, we use the plus sign. And then finally, if we use curly braces, where we can say a number, comma, and then another number, we can define a custom range of a repetition modifier. Next up are the concept of character classes. And a character class is a group of characters that all fit a common pattern or a common theme. So they always begin with a square brace and end with a closing square brace. So any character inside that character class is considered a match. So if we wanted to create a character class of vowels, we would say open square brace, A-E-I-O-U, close square brace. If the first character in a character class is the caret, then any character that's not inside that character class is considered a match. So if we want to create the character class of everything that's not a vowel, we would say open square brace, caret, A-E-I-O-U, in square brace. So ranges can be specified using the hyphen character. So all lowercase ranges are open square brace, A-Z, in square brace. Now ranges can also be combined. So all letters of the alphabet are open square brace, A-Z, uppercase A hyphen uppercase C, close square brace. Next up are the positional characters. Now positional characters don't match characters, they match positions within a regular expression. So if the first character within the regular expression is the caret, that means that the regular expression must match from the beginning of the string. Now if you recall on the last slide, I said that the caret had a special meaning inside of a character class. So remember that the caret has two meanings in regular expressions. Outside of a character class and at the beginning of the string, it must mean that the entire expression must match from the beginning. If the last character in the regular expression is the $sign, that means the regular expression must match from the end of the string. So when used together, where we have a caret at the beginning and a $sign at the end, this means that the regular expression must match the full string in order to resolve as true. So I'm back in my virtual machine, and let's start up a Haskell notebook and review some regular expressions. So Jupyter Notebook starts up our notebook. I'm going to go into my analysis folder where I have all of my notebooks ready, and we are going to declare a new Haskell notebook, and I'm going to name this Regular Expression Overview. Let's import the regular expression library. So it's import text regex POSIX. Now there is a cabal command line which will accompany this video that describes how to install this particular library. Let's create a very small corpus of text. So let text list is equal to, this will be a list where we'll have a string of A's, let's say rabbit, cow, let's have the word Y, let's have a number in a string, 42, and let's have an empty string. And we're going to create a series of regular expressions and match against all of the words in our very small corpus of text. So let's look for any word in our text list that has the letter A in it. So I can map over my list and I can pass in the very simple regular expression A across our text list. And we have a list where we see that the first three items in our list all contain the letter A. And so that means that the regular expression can match anywhere inside the text. So A, the sequence of A's, and rabbit all have the letter A, where the rest don't. Okay, I'm going to be building on this expression, so I'm going to copy and paste it. Let's see if any regular expression has an A followed by a B, but the B turns out to be optional. So we're going to use our first range modifier, the optional character. Once again, we see that the first three elements in the list have an A and perhaps have a B after it. So A doesn't have a B after it, and even though it's one character long, it still matches. The sequence of A's, well, there are no B's, but remember we made B optional, so that's still true. And then we have A followed by a B, and of course that's true because there's a B present there. And none of the rest have an A, and because the A is required and the B is optional, none of the rest are true, so the rest are false. Let's evaluate any word in our corpus that has at least one A, followed by a sequence. So again, we have the same result, true, 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 false, 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 for the rest of the list. So these at a minimum have one or more A's. Now let's change this to A star, which means at a minimum 0 A's. Well, that turns out to be every item in the list. They all return true because they all have at a minimum 0 A's. Let's build on our expression and let's look for any word in our corpus of text that contains a vowel. So that requires a character class. So we say A-E-I-O-U. And we see that the first 4 elements in our list, I'm going to scroll up a bit, contain a vowel. So A, the sequence of A's, rabbit, cow. Y does not have a vowel, according to the character class A-E-I-O-U. 42 doesn't have a vowel, and our empty string doesn't have a vowel. Okay. For our next regular expression, let's look for any item in our list that contains a digit. So a sequence of numbers from 0 to 9 in our character class. Well, there's only one number in our list of numbers, that's the 42 near the end, and so that resolves as a true in our list. And then finally, let's use an example of those positional modifiers. Let's see if we can find a word in our list that consists of all not vowels from start to finish. So what we have to do is use our positional modifiers, and I'm going to back out here. So our positional modifiers are a caret followed by a $, and then inside of there we can build a character class consisting of not vowels. And if you recall that we have the caret sign at the beginning of the caret class followed by the list of vowels, that represents not vowels. And then finally we have an asterisk. So 0 or more characters representing not vowels. So here we have the last 3 values in our list, true, true, true. And we see that the last 3 values in our list are Y, 42, and the empty string. And then finally, let's look for an empty string in our list using regular expressions. And for that, we just use the 2 positional modifiers, caret followed by a $, with nothing in between. And that represents nothing. So an empty string. We see that everything in our list has at least something in it, except for the very last item, which resolves as true. So there is a very brief overview on the power of regular expressions. And I find that I use regular expressions a lot in data analysis in just validating that makes sure all of the values in a particular column meet a standard that I believe should be present. So, in our next video, we're going to cover visualizations. Video 1.4 will deal with visualizations. So in this video, we're going to look at importing the EasyPlot library into our Haskell iNotebook. We're going to be visualizing a dataset as a line plot, and we're going to be visualizing a dataset as a scatter plot. I have started up Jupyter already. I am in my Haskell data analysis folder. Let's go to analysis. We see all of the notebooks that I've created in our past videos. Let's create a new Haskell notebook, and we're going to name this Old Faithful. So let's visualize our data set. So I have a few libraries that I need to import. Let's hit Shift-Enter to make sure they're imported. I need data.list. I need database.hdbc and hdbc.sqlite3. Those need to be installed using the Cabal tool. And then I also have EasyPlot, which also needs to be installed using the Cabal tool. EasyPlot relies on the GNUplot command line utility, so that also needs to be installed in your environment. Now that we've got our libraries installed, let's make a connection to our database. So we will connect to SQLite 3, and Our database, which we made in video 1, is going to be in our data old faithful.sqlite3 folder. Now let's pull our data out. Let's go for the minutes first. So minutes raw, that will get us our raw data. We'll do a quick query of our database, and we will do a select query on minutes from Old Faithful. Add that. Great. Let's do the same thing for eruption. So our eruption raw data. Let's get a quick query of our eruption data. And now what we need to do is to convert this raw format into something that we can work with, preferably the double type. And so let's convert both of our minutes and our eruption data into a type of double. So minutes, and we will map from SQL head. So the first element in each list will be a column entry. And so we'll grab the head of each column, we will pass that to from SQL, and then we will do this for every row in our table. And we should parse this as a list of doubles. So if I hit head minutes, I see that our first entry is 79 minutes. Let's do the same thing for eruptions. So our eruption data will map over each element from SQL head, and then we will pass in our eruption data. And just to make sure that everything is working, the first eruption observation is 3.6. Now, what I would like to do is to focus on the minutes. So the number of minutes between eruptions. Well, let's graph that. So if I just say plot x11, and then we will zip, we need a domain for our data set, and so our domain will just be lazy infinite list of numbers, and then we will pass in minutes. This is our minutes data. So because this is a chronological data set, so 0 represents the earliest data point, and near the end towards 300 represents the later data points, this really should be plotted as a line plot. So by default we get a scatter plot. So let's convert this to a line plot. I'm going to add a $sign here, and let's do a data 2D. We will say that the style of our plot represents lines. We have a second list of style information, which we don't use in this particular instance. And here we have a line plot of our minutes. As you can see, the data is quite noisy, but we do have a way of seeing that the highest data points are between 90 and 100, and the lowest observations are close to 40. Great. Now that we have this visualization, what I would like to do is to plot a scatter plot where we compare each eruption time with its corresponding number of minutes that comes after that eruption. So to do that, let's plot our eruption, where I just take out my lazy list of the domain and I replace it with eruption. So here we have our x-axis, we have the eruption time, where the smallest eruptions were 1.5 minutes all the way up to, it looks like 5 minutes. And then we see our minutes that appear after that eruption, the amount of delay of Old Faithful. And it looks like there is a lower cluster, and it looks like there's a higher cluster, and it looks like there's a gap here in the middle. But we will see what this data looks like in future videos. We'll explore this data some more. So good. We have created a few quick plots in this video, both line plots and scatter plots, and visualized the data. So in our next video, we are going to discuss kernel density estimation. In this video, we are going to explore kernel density estimation. So in this video, we're going to look at understanding the reasons why we might use kernel density estimation to evaluate a data set. We're going to apply the KDE to our minutes column in our Old Faithful data set, and then we're going to explore the results of that KDE. So the kernel density estimation's goal is to explore the shape of data, and whenever I say shape, I really mean the density. Now, if you plot the minutes dataset as we did in the last video, the shape is not clearly revealed by a simple plot. And our goal is to understand that overall shape or density, where values have low density, in other words, when they are spread out, dispersed, versus high density, where they are clumped together. And we can estimate the probability of a particular observation, even if that observation isn't represented in our data set. That's a nice aspect of KDE. In order to do this, we require a kernel function. And that kernel function, in our case, will be the normal. So let's discuss the normal distribution. A kernel must ultimately be smoothed and peaked at a center point. A kernel must also be symmetrical and non-negative. So not only must the kernel be peaked, the kernel must be non-negative, which means that all the values are either 0 or greater. And then the area underneath the curve of the peak created by the normal distribution must be equal to 1. So here we have the normal distribution formula displayed on the screen. There are 3 variables in the normal distribution that you should be aware of. The first of which is x, and x represents the entire domain of our data set. There is mu. Mu represents the observation in which we will be computing the normal distribution. And then we have sigma, and sigma represents the standard deviation of our data set. And I typically treat the standard deviation of our data set to be 1. So what we're going to do with that normal distribution function is we are going to evaluate a normal curve at every observation in our data set for the entire domain of our data set. And we are going to generate lots of normal curves. So our data set with Old Faithful has 272 observations. We are going to generate 272 normal curves. After we generate each normal curve, we're going to add them all together. And then we are going to plot a visualization of what we get. Now, if that normal curve formula looks audacious to you, don't worry, I've already implemented it, and we are going to copy and paste it into our notebook, in which you will have access to. So let's go over to our notebook. I'm going to make a slight change to the import statements on our notebook. I'm going to import data.maybe, and now I am going to scroll down and I'm going to paste our KDE function. So here's our KDE function. I want to describe some of the essential parts of it. We are returning a maybe and then a list of doubles and a list of doubles. Now this is going to represent our domain, the first part, the first return, and the second return is going to represent the KDE itself. So we have the domain and the KDE, and we are taking a list of values. Now if we get an empty list of values, then we're just going to return nothing. That is a benefit of the maybe. But if we get anything beyond a simple list of values, we are going to return just followed by the domain and the KDE. For my domain, I always like to find the minimum value in the list and subtract 5 from it, and the maximum value in the list and add 5 to it. I feel that gives a pretty good domain. It's the full range of the data plus 5 on either side. Here I have the normal distribution formula. That is the very last line in our function. And then here we are mapping our data set over that normal distribution and then adding them all together with fold 1. And then my last step of the KDE is I take that shape and then I normalize the shape. I add up all of the values produced and I divide it by the sum of the shape. Thus, the overall sum of my KDE will equal 1. That will allow me to get the probability of any distribution point. All right, so let's see what this produces with our minutes data set. So I'm going to say just, and then we'll have our domain and our KDE, which I call my KDE, and we'll say KDE of our minutes. All right, now we just plot this. So plot x11, and then I will say zip our domain with a KDE. And now we have a density estimation of our minutes of the old faithful geyser. And we can see that most of our minutes are focused around, looks like the 80 mark. I can see that 81 minutes is a peak, and I see that 77 minutes is a peak, and there's this conspicuous little gap between those two. I also see another peak at around 52 minutes, and there is a minor peak at around 58 minutes, and another peak at around 45 minutes. And we see other minor peaks, say 87 minutes, scattered around the data. And anything that represents a low point from there represents an entry where there's just not a lot of data. So there's low density at around 66 minutes. And we see the overall shape of the data. Now, the next time Old Faithful goes off, what is the probability that we will see 81 minutes? Well, I can just hold my mouse pointer over it and see that it will be at about 0.46%. So 0.46% of the time I will see 81.49 minutes, or 81.5 minutes represented. So that sort of gives you the density and shape of our data set. I like to use the KDE as an alternative to histograms. All right, so there's our KDE of the shape. It's time for our section review. So a summary of section 1. In video 1, we converted a data set that I found online. Blooper. So in video 1, we converted a data set that we found online. We built a CSV file out of that format, and then we converted that CSV file into SQLite 3. We visualized that data set with the EasyPlot library. We took a moment and discussed the basics behind regular expressions, and then we implemented and evaluated the KDE of our minutes data set. So in our next section, we are going to start discussing a more advanced topic, linear regression. In section 2, we will be discussing regression analysis. Regression analysis is the study of how variables relate to each other. So in this section, we're going to take a look at linear regression. We're going to follow that up with an understanding of the correlation coefficients that go into understanding a linear regression. Linear regression is far from perfect, so we're going to have a video devoted to the drawbacks of linear regression. We'll be discussing logarithmic regression and polynomial regression as well. So video 2.1 is on linear regression. So linear regression is the study of how two variables relate to each other, where we try to model that relationship with a straight line. So in this video, we're going to be describing our United States population data set and what went into that data set. We're going to be performing linear regression on that data set, and we're going to be estimating a data point using linear regression. So linear regression attempts to find the relationship between two variables using a linear relationship. And anytime you hear that word linear, you should be thinking it's a straight line. So here we have the formula for a line. Y is equal to a plus bx. Now we should be understanding the parts of this formula. We have x, which is our independent variable, and independent variables within a data set are the ones that we don't believe are related to each other. In this case, with the population of the United States data set, our independent variable is the year. We also have the dependent variables, and those are columns within our data set that we believe depend on our independence. And in this case, that is our column Y, which is estimated. And this will be the population itself. We also have two constants in our formula, A and B. A represents the intercept of a line and where it crosses the y-axis, and B represents the slope of a line. So here is a plot of the United States population according to the United States Census from 1790 to 2010. So according to the United States Constitution, every 10 years, the government is required to take a census of the people. Now, what determines the people has changed in definition over time. At the founding of the country, those were U.S. citizens and indentured servants and slaves, but the slaves counted for 3/5 of a full person, whereas a free person and indentured servant counted as a full person, and Native Americans weren't counted at all. Nowadays, everyone is counted who lives in the United States as a full person, and that includes free persons, that includes Native Americans, and that includes non-citizens living in the country long term. So in order to compute the linear regression of a data set, we need to understand a few terms, including the covariance and the variance of variables. So covariance is a measure of how two variables change with respect to each other. So if we have two variables and they change positively, in other words, if one goes up, the other goes up, then the covariance score will have a positive value. Likewise, if we have two variables and if one goes up, the other goes down, they have a negative relationship, then the covariance score will have a negative value, and we have the formula presented here for the covariance. The variance is a measure of the spread of a variable from its mean, and it turns out that the formula for variance is based on the covariance, and so we have the formula for variance presented here. All we're doing is calling the variance with the input of the variance twice. So now that we have a very brief cursory understanding of covariance and variance, we can use those two properties in order to understand the gradient. And if we have the covariance of two values, an x and a y, that is the year and population of our data set, we take that covariance and we divide by the variance, in other words, the variance of our year, and that becomes the gradient of our line. The intercept of our line is now based on the gradient, where we take the average of our population minus the gradient times the average of our years, and that becomes the y-intercept. And now we have enough information in order to perform linear regression. So I'm back in my Jupyter Notebook window. I have created a notebook called Linear Regression, and I've already typed up the code in order to build the population data set and then plot that population data set. And I have two variables being plotted, the year and the population. So the year is represented on the x-axis, going from 1790 to 2010, and then we see the growth in population over time. And those variables are represented by year and population. And that's all we have in our notebook so far. So we need to create a few definitions, and I'm going to start off with the definition of average, which is the sum of our values divided by the length of our values. We need the definition of covariance, so let's type up the covariance formula, the Haskell version of it, quickly. So that is going to be the average of our mean adjusted data set. So let's pass in a quick lambda function into zip width xi and yi, and we will mean adjust those two values and then multiply them. And then we will pass in our two lists, so xs and ys. And then for our third definition, we need the variance. So the variance xs is just covariance of xs twice. All right, that's straightforward. Now, because linear regression is a little bit longer, I'm just going to paste this into the window to make sure I type it correctly. So here we have the definition of linear regression. We take a list of doubles which represent our independent, and then a list of doubles which represents our dependent, and we get back a gradient and an intercept, where the gradient is simply the covariance of our two variables divided by the variance of the independent, and then our intercept is the average of the dependent minus the gradient times the average of the independent. And so there is our linear regression. So let's go ahead and call linear regression on this data set. So we have our gradient and we have our intercept. So we have our linear regression of the year and the population. So let's check out the gradient and the intercept. So these variables represent how the line is formed. So every year, the United States population seems to grow about 1.4 million. And here, if we were to go back in time, the population of the United States at year 0 would be negative 2.4. So that is a nonsensical value. But hopefully you can illustrate some of the pitfalls of linear regression just by looking at that variable. But let's go ahead and plot this line. So what I would like to do is form the regression line. So our regression line is going to be a mapping of our regression formula, in other words, the gradient times x plus the intercept for our years. So that forms the regression line. Now I'm going to scroll up and I'm going to grab our plot line that I wrote earlier before this video in order to plot the United States population. And I am going to add another data 2D, and this will be a style lines, and we're going to title this US population estimated, our year and our regression line. So our green line here represents the line of best fit for this particular data set, where we try to minimize the distance between a data point and the line across the entire data set. So some of these match very close, and some of these barely match at all. So using this regression line, we should be able to estimate what the population of the United States is in the current year. So let's go ahead and do that. So the current year is 2016. So the current year is 2016. We multiply that times the gradient, and we add the intercept. So according to this, we see that this is raised to the power of 10 to the 8. So the population of the United States is approximately 260 million. Now we know that the population of the United States in 2010 was 308 million, which means this is undershooting the current population of the United States. It's one of the pitfalls of linear regression. And we're going to explore these pitfalls in future videos. But hopefully you get an idea of the benefits of linear regression and how it's used to estimate. In our next video, we will be discussing correlation coefficients. In this video, we are going to discuss the correlation coefficients of regression analysis. So in this video, we're going to take a look at the Pearson R coefficient. We're going to discuss the R squared coefficient, and then we're going to be computing the R and the R squared coefficients on our United States population data set. So this is the plot that we generated in our last video. It's the United States population from 1790 to 2010. In the red dots that appear, those are the actual data points, and the green line that appears is our estimated regression line. So our estimated regression line shows that at the most recent end of our data set, the estimated line is clearly got a gap between the actual data point and the estimation. Whereas on the other end of our regression line, we see that there is another significant distance. In fact, you can tell on the plot, there's 0 representing a 0 population. According to our estimated regression line, the United States population is effectively 0 up until about 1825. So in order to evaluate our data set, we need to understand the covariance and the variance and the standard deviation. So the covariance and the variance are the formulas that I introduced in the last slide. And what I would like to do is to add the standard deviation formula. And all it is a square root of the variance. And like the variance, it is a measurement of the spread of a variable from its mean. So let's introduce the Pearson R coefficient. So the Pearson R coefficient is a measurement of dependence. In other words, if we have two variables and both of them increase respectively, well then we should have a positive coefficient. Whereas as one increases, the other increases. Now if one increases while the other decreases, that means we have a a negative relationship. So a -1 means that there is a complete negative correlation between our two variables, whereas a +1 means that there is a complete positive correlation. Now these are ranges of values, meaning that you could have any value between -1 and 1. And if you get a value perfectly in the 0, that means there is no correlation at all between these two values. So I have to introduce a warning. Interpreting these values beyond the description is a subjective art form. So aside from those three definitions, any other description really is subjective. And more often than not, you're going to get a value that is not one of those three values. So here is the formula for the Pearson R coefficient. It is the covariance of our two variables divided by the standard deviation of one times the standard deviation of the other. Now the Pearson R squared coefficient is a measurement of determination. In other words, it tells you how strong the correlation is between two variables. And all it is a squaring of the Pearson R coefficient. Because it's a squaring, it will always be on the range of 0 to 1, where 0 means that there is no correlation at all, and 1 means that there's a perfect correlation. So here I have to introduce the second subjective warning. Any interpretation beyond the values of 0 or 1, again, is a subjective art form, and again, you're going to see those values more often than you'll see a 0 or 1. So let's go over to our notebook. So I'm back in my notebook. I already have my covariance and variance definitions in my notebook. Let's go ahead and add standard deviation. So the standard deviation is the square root of the variance. Now let's go ahead and add the Pearson R, and that will be the covariance of the two variables divided by the standard deviation of 1 times the standard deviation of our other variable. And now we need to introduce the Pearson R square. So the Pearson R squared, I'm going to abbreviate that SQRD, and that is simply a squaring of the Pearson R. So we'll say the Pearson R with xs and ys, and then we can just say to the power of 2. So let's go ahead and compute our values for the year and the population to see how strong our data set is. So the Pearson R of our year and our population is 0.95. So that is a value that is very close to 1, and we are going to determine based on that value that there is a strong positive correlation between the year and the population. So let's compute the Pearson R square. Based on that, we get 0.92, and again, that is a number very close to 1. And based on that value, we can determine that there is just a strong overall correlation between the year and the population. So is this correlation between the year and the population noise, or is there a relationship between the two variables? And because this value is closer to 1 than it is to 0, I'm going to say that yes, there is a relationship between the current year and the population. Again, this is a subjective art form in interpreting these values, and so another person may come along and say something otherwise. But based on a score that strong, I really doubt it. So in our next video, we are going to discuss the drawbacks to linear regression. This video will discuss the drawbacks to linear regression. While linear regression is a commonly used tool, it is not a silver bullet, and so it's important that you understand the pitfalls of the procedure. So in this video, we're going to take a look at the history of Anscombe's quartet. We're going to take a look at the mean, standard deviation, linear regression, and the coefficients of this particular data set, and then we're going to plot the data set. So this is a special data set, Anscombe's quartet. That's really a collection of 4 data sets that was created by Francis Anscombe in 1793. And the purpose of the creation was to illustrate the pitfalls of linear regression. So each data set has an independent variable column and a dependent variable column. There are 11 observations in each column. So we have 4 data sets times 2 random variables times 11 observations each for a total of 88 values. And the purpose of the dataset is to emphasize why we study the visualizations of the dataset before we perform the regression analysis on that dataset. And so because we should study the visualizations first, to illustrate this point, we are going to look at the visualizations last. So here is the full dataset, and it's a small enough dataset that we could put it on a single slide. You'll notice that it's grouped into 4 sets. We have set 1 to set 4. Each has an independent column and a dependent column, and there are the subsequent values in each column. And so there's no contextual information that goes along with the dataset. You just have to look at the values. So let's look at the values. Now these values will be supplied in a SQLite 3 database that will accompany this video series. So I'm back in my notebook. I have created a notebook that I have titled Linear Regression Drawbacks. We have imported the EasyPlot library and the SQLite 3 libraries. I've made a connection to my regression SQLite 3 dataset, and I have 4 tables which I have created, set 1, set 2, set 3, and set 4, and each of these have an X and a Y column in them, and I have parsed out the X and the Y. Likewise, all of the mathematical definitions which we have been using in this particular section have all been lined out in this series as well. So we have our average, covariance, variance, linear regression, standard deviation, Pearson R, and the Pearson R squared. So I would like to get started by creating a data set of just the X columns. So let X list is equal to our X columns, and I've named them X1, X2, X3, and X4. So those are just the independent variables. Now let's do one for our dependent variables. I'm going to call that the Y list. Great. So we have our dependents and we have our independents all lined up. Let's go ahead and compute an average of each of our independents. So that's our X list. We can do that quite easily by mapping our X list over average. Now if you look at the 4 values, we see that all of the independents have an average of 9. Great. Let's look at the Y values. Alright, so there's a little bit of floating point rounding going on in this particular result, but you can see that they all have an average of about 7.5, and those are for our dependents. Now, do they have the same standard deviation? Well, let's find out. So map standard dev over our X list. So our independents all seem to have an average of about 3.16, and you can see that 4 times for each of our 4 data sets. Now let's explore the dependents. And you can see that they each have a score of 1.936 or 7 thereabouts, but 1.93. Each of these data sets are very close in terms of their average and their standard deviation. Now let's go ahead and compute the Pearson R score, which determines if they have dependents and our independents have a strong linear correlation. For that, we can use zipwit. So zipwit, we're going to look at our Pearson R, and we will pass in our X list and our Y list together. And so now we've generated the Pearson R coefficients for each of our 4 data sets. And they each appear to have a correlation score of about 0.816. Okay, and so 0.816 indicates that there is a good linear correlation, maybe not a great linear correlation. Now let's perform the linear regression on each of these data sets. Perhaps we'll see something different here, but we're looking to see what the gradient and the y-intercept of each of our 4 data sets should be. So let's use zipwidth again, and we'll pass in our linear regression. And let's pass in our X list and our Y list. Now again, there's a little bit of floating point rounding going on here, but you'll see that for each data set there's a pair of values. The first value is the gradient and the second value is the y-intercept, and they all appear to have a gradient of 0.5 and they all appear to have a y-intercept of about 3. All right, so we have looked at each of these 4 data sets with the average, the standard deviation, the Pearson R, and the linear regression, and they all appear to have virtually the same values. So if we were to plot this information based on just a cursory look at these statistics, we should conclude that they're all roughly the same visualization. And let's find out if that's true or not. So let's do a plot on X11, and we are going to map our data sets over a data 2D. To make things simple, I'm just going to pass in the bare defaults. We are going to uncurry and zip, and then we are going to zip again the X list and the Y list. So this particular zip that I'm highlighting zips the list together, but that's not the format that's needed by plot. And so there we immediately uncurry what we've associated together, and then we zip it up in a second way. So let's plot this information. So here we see the full plots, and you can see values just scattered all over. And so every single color represents a different data set. So let's take in particular the red dots, and you can see the red dots scattered through here. That's our data set number 1, and they're just a scattered data set that appears to be noisy. Now our green dots, if you study the green dots, there's a green dot there, and they seem to have a curvature pattern right there. So those green X's, there's a nice general curve there. Let's look at plot 3. Plot 3 is a straight line. Just a boring old straight line right through the middle of our plot. But wait, we've got one outlier way up here. And then finally, we have our 4th data set. It's a 4th plot. It's just a set of purple dots that are all in a vertical line. With one exception, there is an outlier, and that outlier appears way up here in the key of our data set. You'll see that I've got it highlighted up there in the crosshairs. Right there, that's not part of the key. That's actually one of the data points to our data set. It's way off over here, apart from the whole rest of the data set. So what Francis and Scombe was trying to do with this data set is to emphasize that data sets could have wildly different visualizations and misleading Pearson R-scores and regression coefficients. So what you should really do is to plot those visualizations first before you attempt to make sense of the data by way of regression. So our next video will cover logarithmic regression. In this video, we are going to look at logarithmic regression, and we're going to return to our United States population dataset that we looked at in videos 1 and 2 of this section. So in this video, we are going to be introducing logarithmic regression. We're going to be performing logarithmic regression on our United States population dataset and seeing if it reveals a better model for our data growth than linear regression. And then we're going to be plotting the logarithmic regression of our dataset and comparing it to the actual population growth. So in video 1 of this section, we plotted this graphic where we performed linear regression on our dataset. And you can see that we have the green straight line population estimate, but the actual growth of the population is more of a curved line. And because a curved line is noticeably different from a straight line, there's a very good reason to argue that the population growth of the United States is not linear. So what's going on with this data set? It's safe to say that the United States population growth isn't linear. It might be that the population is growing exponentially. So here's just an idea that we're throwing out. So in order to study an exponentially growing data set, or even one that we think is growing exponentially, there's a 2-step process. First, we compute the log of the dependent variable, and then we perform the regression analysis as normal. Now, the reason why we go with a log of the dependent variable is because we believe that this is an exponentially growing data set, and logarithms are the inverse of exponents. So in video 2 of our series, we looked at the Pearson R and the Pearson R squared correlation coefficients. And I have listed here our coefficients that we recorded from that video from linear regression. The Pearson R was 0.96 and the Pearson R squared was 0.92. And we're going to see how this compares whenever we compute the logarithmic regression of our data set. So I'm back in my linear regression notebook. I'm going to take an opportunity to rename linear regression to simply regression, because this is now a regression notebook and we're not focusing on just one type of regression. So let's begin by performing the log of our dependent variable. So we'll call this the log population. And we simply say map log population. Great. Let's now perform the linear regression of the log of our data set. So log gradient and log intercept is equal to linear regression of the year and the log population. Let's look at those coefficients that were developed. There's our log gradient coefficient and our log intercept. Next, let's create the log regression line. Now, because we're treating a logarithmic regression as a linear regression, if I were just to plot these coefficients as a straight line, well then it would obviously be a straight line and that wouldn't give us any benefit. In order to compute the log regression line, what we do is we compute what we believe to be the estimate of our regression line, and then we take that list of values and we raise those values as the exponent of natural E. So the function for natural E is exp. Log regression is a mapping where we will pass in our x, that will be our year value, and we will say exp, and we will say our log gradient times our x plus our log intercept. And we'll pass in our year. So that is the log regression line. Let's go ahead and plot what our log regression line looks like. So I'm going to scroll up a little bit. I'm going to find our previous line where we plotted a regression line. And I'm going to scroll down. I'm going to paste it here. And all I'm going to do is I'm going to change regression line to log regression line. So here you see the logarithmic regression of our data set. We now have a curved line which maps over our curved line data set. You can see that at the smaller values we got a very good mapping. There's a little bit of a good mapping here in the 1950s and 60s, but there seems to be a departure in the middle of our plot, and there is a significant departure in the more recent years of our plot. I'm looking at this plot and I don't think we got a better result from our linear regression. But let's see what the Pearson R and the Pearson R squared coefficients tell us. So let's compute the Pearson R and the Pearson R squared coefficient. So Pearson R, year and log regression line, 0.88. That was not as good as what we got from the linear regression. And Pearson R squared, 0.77. No, I believe these regression lines were actually worse. I believe that this regression line is actually worse than our regression line formulated in videos 1 and 2. But let's go ahead and estimate our current year population. The year is 2016, based on this particular information. So we say exp, and we type in log gradient times 2016 plus log intercept. We have a value of 532 million as our estimated population. Now the current realistic estimations of the population of the United States is 322 million. So this is a full 200 million more than the actual estimate. This is significantly off. So we can safely say that the population of the United States is not exponentially growing. So I have listed the new logarithmic regression column on our table. Our Pearson R and Pearson R squared values are 0.88 and 0.77. this was worse than our linear regression line, and we can safely say that our problem is not solved. We can explore at least one more model to see if we can get a better result. And that's what we'll be doing in our next video on polynomial regression. In this video, we are going to examine the third and final type of regression that we will cover in this section, and that is polynomial regression. So in this video, we are going to be introducing polynomial regression. We're going to be installing the necessary libraries for polynomial regression. Polynomial regression is going to require linear algebra, and there are linear algebra libraries in the Haskell language that will make this so much easier on us. We're going to be performing polynomial regression on our United States population dataset, and we're going to be plotting that polynomial regression line on our United States population dataset. So here is our regression table so far with the two previously introduced types of regression. We have the linear regression line and the subsequent Pearson R and R squared coefficients, and the logarithmic regression and the R and R squared coefficients. We found that the linear regression line tends to be the better result of the two types of regression that we've encountered so far. We're going to introduce polynomial regression and see if it does better or worse. So what kind of growth could this be? We have a mystery on our hands. We don't know the underlying model that we could use in order to illustrate the population growth of the United States. Is it linear regression? No. We know that the growth is a curved line, and linear regression only reports straight lines. Is it logarithmic regression? No. We found that logarithmic regression actually performed worse than our linear regression. Is it polynomial regression? Polynomial? Maybe. So let's perform a regression on our data, assuming that the growth rate of the population of the United States follows a second-degree polynomial. Now let's introduce polynomial regression. So polynomial regression assumes that the dataset follows a polynomial formula. And so I have a relatively simple polynomial equation presented on the screen, y equals ax squared plus bx plus c, and this is a second-degree polynomial. So throughout this video, we are only going to use second-degree polynomials, but you could expand this out to potentially any degree polynomial. Second degree is just easy to demonstrate examples with. So the particular line which I have graphed on the screen has three parameters to it, a, b, and c, and in this case the a is set to 1, the b is set to 0, and the c is set to 0. And our goal is to figure out what three variables, a, b, and c, best match our United States population dataset. So it turns out that this is a linear algebra problem. So in order to fit our coefficients into the form ax squared plus bx plus c, we need to follow this particular pattern. And so you'll have a vector on the left side of our equal sign. You'll notice that's just a sequence of our y points. And then we have a matrix of our x values. And so the first row is just going to be x1, and the second row is just x of 2. And the last row is whatever the last x value is. Now each column is going to be all of our x values raised to the power of whatever index of that column is. And the first index is raised to the power of 0. Now you should know from your mathematics classes that anything raised to the power of 0 is 1. So that first column is really just a sequence of 1s. Anything raised to the power of 1 is the value itself. So that second column is just the x values themselves. And now we have the third column, which is x values raised to the power of 2. And so here we have our x values squared. Those columns are going to be multiplied by the matrix CBA, where C, B, and A are the parameters to our second-degree polynomial that we're trying to discover. We can simplify that equation. You'll see it at the bottom of the screen. We have a y vector which is equal to an x matrix times the matrix of CBA. So in order to determine our coefficients, we need to solve for our matrix CBA, and for the lack of a better variable name, I call this matrix P. So in order to solve for matrix P, we have this formula here, and you'll see it's x transpose times x, and then we invert it times x transpose times y. That does look like a rather difficult formula to go through, but with the linear algebra libraries that we are going to install, that formula actually becomes trivial to implement. Once we have discovered p, the parameters of our polynomial, a, b, and c, are the elements of p. So the first element in p is going to be c, and the second element in p is going to be b, and the third element in p is going to be a. From that, we can determine the regression line, and from there, we can plot and analyze the data. Now, I've already installed the necessary libraries on my Linux virtual machine, and here's where I want you to pause the video, go over to your work environment, and set up your virtual machine. You're going to need to install the LPACK and the BLAST libraries. And conveniently, it's one line of Debian code, sudo apt-get install lib-lpack-dev. That will install both of those libraries for you to work with the BLAST and the LPACK environment. Now, in order to download the Haskell wrappers, you need to use Cabal and install HMatrix. So HMatrix is really a wrapper for the LPACK libraries. Once you've executed those two lines on your system, you should be good to go. You may have to reload your iNotebook environment, but once you do that, you're good. So let's go over to our virtual machine. So I'm back in my virtual machine. I am now at the top of my notebook, and what I would like to do in my very first line where I have my imports, I need to add two imports. So I am adding numeric.linearalgebra.data, and I'm adding numeric.linearalgebra.hmatrix. Once you've added those two lines, you'll have to restart and rerun all on your notebook. So that's going to reload all of your variables, and you're going to see the images from past plots that we've done appear. Great, we're good to go. If you recall from our slides, the first row in our data set is simply the first x value raised to the power of 0, and then raised to the power of 1, and then raised to the power of 2. So what I would like to do is to create a simple helper function in order to assist with that small operation. So we're going to call this power. So power xs is equal to map pow, and then we'll say xs raised to a pow. This way I can pass in a power, and I can say 2, for example, and I can say 0 to 2, and we have 2 raised to the power of 0, 2 raised to the power of 1, and 2 raised to the power of 2. So you sort of get the idea of what that particular function does. Next, we need to build our x and y matrices. So typically mathematicians will write capital letters for matrices, and this is not something that Haskell will allow us to do. So I'm going to use ym for our y matrix and xm for our x matrix. Now ym is just a one-column matrix. So there is a trivial way to do this. We say ym is equal to matrix 1 population. And that 1 means we have a matrix with exactly one column. And we can explore this matrix. So those are our data points. And you'll see it's just the current values of the population of the United States. Next, we need to build that large x matrix. So xm is going to be a matrix. Because we're working with a second degree polynomial, there needs to be 3 columns, and so we'll say 3 right here. And what the matrix constructor requires is just a very long list in row order format. So in order to create that very long list in row order format, we're going to use concat_map. So we're going to be generating a list of lists, and then we're going to ask concat_map to convert it to one long list. And so we're going to call on our power function that we used earlier, and we're going to map it over the list 0 to 2, and we're going to pass in our year. Let's view the xm matrix. And you can see that the first column is all ones, the second column is just the years themselves, and the third column are the years squared. And then I'm going to scroll up a bit and you can see that line there. We're using concat-map just to make a long list, and we're piping it into the matrix constructor to make sure that we have exactly 3 columns. Let's keep going. Now that we have our X and Y matrix, we need to perform that long linear algebra equation that I showed you in the slides to generate our P matrix. I am going to set P is equal to the multiplication of the inverse of the multiplication of the transpose of our X matrix times itself. So here we have the multiplication of the transpose of X and X, and then here we take that result and we invert it, and then we are going to, as our second parameter to the mul at the beginning, we need to pass in another mul where we transpose X, and then we pass in our Y matrix. That's the line. So there's all the transposes and the inversions and the multiplications in one line. And we generate our P matrix. And so here are our P coefficients. It's simply a 3x1 matrix in size. This value is our C, this value is our B, and this value is our A. So now we need to pull these out of the P matrix, and in order to do that we use @index. So C @index P, and we can ask for the first value at 0, 0. And you can see that we have 2.1987, 2.1987. There we go. And we do the same thing for B, which is at 1, 0. There is our negative 2.44, negative 2.44. And let's do the same for A. And the value we're looking for is 6,785.59, 6,785.59. Great. So we have our A, B, and C parameters now for our polynomial regression. Let's compute the regression line. So we'll say the poly regression line is going to be equal to a mapping where we're going to map our years to our formula. So that's A times X plus B times X plus C. We'll pass in our year. There's our polynomial equation. So we've just created the polynomial regression line. Let's plot that polynomial regression line and see how close it gets to the actual data set. So I'm going to scroll up and find the last time I plotted a data set. Right there, where I did the log regression in a past video. And I'm going to change log regression to poly regression. That seems to be a good model. There seems to be almost no departure at any point along the line between any of the real data points, which are the red values, and the estimated line, which is the green line. Now there is a slight departure in the 1940s and the 1950s. There was a dip in the population there that seems to be out of place. But other than that, I think this is an excellent model. So as I said in the last video, the current estimate for the population of the United States is 322 million. Let's see what the population of the United States is according to our second degree polynomial model. So we say A times 2016 times 2016 plus B times 2016 plus C. According to our new polynomial regression, the estimated population of the United States is 323 million. And as I said, we currently believe the population is 322 million, so only a million off in our estimates, whereas our past estimates were over 100 million off in both cases. Let's compute the Pearson R-squared coefficients in order to end the video. So the Pearson R-squared coefficients of our year and our poly regression line we have 0.96, and the Pearson R-square is 0.92. Those values may seem familiar. I am back in my slides. I'm going to add my new column to my table for polynomial regression, almost the same values as what we had for linear regression. So while polynomial and linear regression had equivalent coefficients for the Pearson R and the Pearson R-squared coefficient, that polynomial regression formula gave us an estimate for the current year's population of the United States that was almost a bullseye. If I had to stake money on the three types of regression that we have covered in this section, I would argue that the growth rate of the United States follows, at the very least, a second-degree polynomial. Now, you can extend the approach out to what we did today to third and fourth and n-degree polynomials, and you may find results that are better than the second-degree polynomial that we witnessed today. There is a danger in finding the perfect solution to the point that you overfit and that you don't allow for new data, because the new data will mess up the model. So it's good to aim for accuracy, but at the same time you shouldn't be so accurate that you're damaging the ability to take in new data. So let's go over our section summary. In video 1, we performed linear regression on our United States population data set. We explored the correlation coefficients of that linear regression in Volume 2. In Volume 3, we detoured and explored the famous dataset known as Anscombe's quartet. We took a detour in Video 3 and explored the Anscombe's quartet, which is a purposely built dataset in order to emphasize that our datasets need to be visualized before we perform regression. So this particular dataset is visually different while mathematically similar. In Video 4, we returned to the United States population dataset and explored the possible growth rate, and we explored the idea that it was logarithmic. It's not. And then finally, we performed polynomial regression on our United States population dataset. That turned out to be our best result and gave us a highly accurate estimation of the current year. All of this that we've been discussing is regression of a single variable. We only had a single independent variable and a single dependent variable. Now, what would happen if we branched out to more independent variables that impacted a single dependent variable? Well, that's going to be the topic of conversation in our next video series, multivariate regression. In Section 3, we will cover the technique of multivariate regression. In this section, we're going to take a look at putting together a dataset for the purpose of multivariate regression. Preparing our dataset is a tedious yet important task, and we're going to devote an entire video to it. In our next video, we're actually going to perform the multivariate regression and discuss the math involved. In video 3, we're going to be calculating the adjusted R-squared score, which is reminiscent of the R-squared score that we discussed in section 2. And we're going to take a closer study of the adjusted R-squared score. So this video is devoted to building matrices. So in this video, we're going to describe the movie lens dataset. It's the same dataset that we covered in section 6 of beginning Haskell data analysis. If you did not purchase beginning Haskell data analysis, that's fine. The dataset has been included with this video series, packaged in the SQLite 3 format. We will be describing the process by which we craft matrices in HMatrix, and then we'll be preparing our movie lens dataset for multivariate regression. So I'm back in my virtual machine, and I've done a search for movie group lens, and I have found the group lens website. It's at grouplens.org, and I'm at datasets movie lens. And there are several datasets on this website, but we're going to be concerned with the first one. This was released in April of 1998, so these movies tend to be a bit older. There are 100,000 ratings from 1,000 users across 1,700 movies. And let's explore the README file that is accompanied in the dataset. So there are three important tables that need to be discussed in this dataset. The first is called data, which contains all of the ratings. the second of which is called item, which contains the movie metadata, including every single genre that each movie relates to. For each movie, if a movie is a part of that genre, there will be a 1 in that column, and if it's not part of that genre, it'll be a 0. So it's a binary representation, and a movie can be in several genres at once. The third table that's in this dataset is user, and this contains all of the information about the users who perform the ratings found in the data table. We will not be using the user table in this section, but we will in future videos. So I've got a notebook set up already called multivariate regression. I've got the data.list library imported, I've got the database libraries imported, and I've got the numeric linear algebra data and HMatrix libraries imported. We used those libraries briefly in the last video. I have made a connection to the database, and let's begin by going over a few variations on how to create matrices in HMatrix. The primary command for creating matrices is matrix. There are two variables to pass in. So we begin with matrix. We describe the number of columns we wish to have in our matrix. So if we want a 3-column matrix, we can pass in a 3 followed by the data that we wish to be in that matrix. And so you can see it's in row order format. We have the values from 1 to 15 in a 5 by 3 matrix where we have 1, 2, 3 all the way down to 13, 14, 15. The column must be a multiple of the length of your data set. So I can say matrix 5, 1 to 15. So we have a 3 by 5 matrix. If I wish to create a column matrix, I simply put in 1 column. So here is a column matrix of 5 by 1. And if I want a row vector matrix, I simply put in the number of columns equal to the length of my data set. So I can say matrix 5 and 1 to 5, and I now have a row vector matrix. Now let's begin looking at our movie lens data set. Now I'm going to switch back over to my terminal here, and I'm going to enter my data filter, and I'm going to do a SQLite 3 on my movies. Let's look at the tables. I have 3 tables in my database, data, items, and users. Let's look at the schema for items. So the schema for items includes every single genre that a movie might possibly be a part of. Well, let's look at the schema for data. And here we have the ratings of each movie. Now in the items table, the first column is movie ID. That corresponds to the item ID in the data table. So if a rating contains a number here, the same number will match to a movie in the items table. That's important to remember for what we're going to do next. So let's begin. I like to introduce a read column function where we map over the from SQL function so that we can parse data out of our database. Now what I would like to do next is to build one giant matrix of all of the movie genres. And this is a long command, so I am just going to paste it into the notebook here. The data that we're storing is going to be stored in raw, and I'm making a quick query to our database where you'll see that I have listed every single genre that is supported by our data set, and it ends with Western right here. We are going to order by the movie ID, and we are pulling from the items table. So this is a rather large data set that was just loaded into our notebook. We're going to build our data set by parsing this into a list of doubles, and I'm going to call this list the full. So we're going to map over our read column function, And we're going to be pulling from raw, and we're going to have a list of doubles. That should be an equal sign right there. Good. Now, the very first record in the items table is the movie Toy Story. So let's look at Toy Story's record. So I can do head full, and we see the genre information for the movie Toy Story. Toy Story, if you've ever seen the movie, is a children's animated comedy movie. And sure enough, if you look right here, there are ones back to back right there. So 1, 2, and 3, 4, 5. Whatever 3, 4, 5 are should match up with the movie Toy Story. And if I look here, 1, 2, 3, 4, 5, animation, children's, and comedy, well, those all correspond to 1. And everything else is a 0. So Toy Story is an animated children's comedy. We can look at the length of our data set. We see that we have 1,682 rows, which corresponds to the README file that we looked at earlier. And we see that there is a length of 18 genres that are represented in this data set. Now, in order to prepare our table, there is yet another method of creating matrices that I didn't discuss. And because this is a list of a list, there is a quick and easy way to create matrices from a list of a list, and it's called from list. So from list, and list is plural, we can pass in our full, and that will create a matrix that is 1,682 elements by 18 elements. So let's calculate how many elements that is. So 1682 times 18, we get just over 30,000 elements. I'm not going to present that whole blooper. I'm not going to present that whole table on the screen because it's going to fill up the entire screen with data. This is actually not the way to prepare our data set for multivariate regression, and I'll explain why in the next video. But just for the purpose of creating a matrix based on the data set, this works great. We're going to modify this line in the next video. So let's work on the dependents. The dependent information I would like to study is going to be the average movie rating. And for that, I'm going to rely on the average function that's built in the SQLite 3. So I'm going to call this the dependent raw data. We're going to make a quick query to our database where we select the average rating from data, and we're going to group by the item ID, and we're going to order by the item ID. Now notice that both of our SQLite 3 queries have an order by and then whatever the movie ID is. That way we keep all of our records in order across both data sets, the independents containing just our genre information and our dependents containing our movie ratings. From here, let's make a quick check to make sure that the number of rows in dependent raw matches the length of our genre information data set. So we should get a data set that has a length of 1,682 rows. So length dependent raw, great, 1,682 rows. That's exactly what we needed. So let's build our dependent data set. So we're going to transpose the dependent raw data set. We're going to take the first row of that transpose, and then we're going to convert it all to a list of doubles. Did I misspell transpose? There we go. Next, we are going to build our dependent matrix, which I'm just going to name D. And because this needs to be a column matrix, I'm just going to pass in a column of 1. Great. Our data set is ready for multivariate regression. In our next video, we're going to be performing multivariate regression. In this video, we will be performing multivariate regression. So in this video, we're going to take a look at describing the process of multivariate regression. We're going to be performing multivariate regression on our movie lens data set. We're going to be understanding the results of that regression. So what is multivariate regression? Multivariate regression is the study of how two or more independent variables impact a single dependent variable. So in our movie lens dataset, our independent variables are our 18 columns of genre information. We've gone from one independent variable to 18, and this could be expanded out to any number of, but ultimately we have to study exactly one dependent variable. And in this case, our one dependent variable is the average movie rating of a movie. The coefficients produced by the multivariate regression will tell us if an independent variable has a positive or a negative or a negligible impact on a dependent variable. So we're looking to see if a genre of a movie based on just the genre by itself helps the movie rating, hurts the movie rating, or doesn't really have an impact. I'm sure the results will surprise you. So we're going to answer the question, how much of an impact does a movie's genre have on the enjoyment of that movie? In other words, do people appreciate action movies just because they're action movies more than regular movies? Do people appreciate comedies more than other movies just because they're comedies? Or do people like action movies less just because they're action movies? We all have opinions on this particular matter, but we're going to look at the data and see if there's any evidence to support these suggestions. So our data set is going to be reminiscent of this matrix. We're going to have two matrices. One is going to be what I call the D matrix, which is our matrix of dependence. It's a column matrix consisting of n rows representing the number of dependent observations. And in this case, n is going to be equal to 1,682, which are the number of movies that we are studying. Likewise, our independent matrix will also have n rows. So our data set will have 1,682 rows. But our column is going to require the number of independent variables plus one column. Because we are studying 18 genres, our matrix is going to require 19 rows. And that 19th row is going to be all ones, and it's going to represent intercept, at which our data starts off at. Now in video 2.5, we had an intercept row, and that was the very first row. And in this case, we're going to have an intercept row also, but I'm going to stick it at the very end. Now I suppose it doesn't really matter where you stick the intercept row as long as you remember where you put it. So in this case, our intercept row is going to be the last row in our matrix. And we're going to multiply that matrix times an unknown matrix P. And P will be a matrix that has one column and m plus 1 rows, where m is the number of independent variables. And we need to discover what that P matrix is in order to solve our problem. So solving our system. In order to discover P, we're going to have to solve this particular equation. Now if you'll notice that equation, that is identical to the equation that we saw in video 2.5. We're going to be implementing this formula yet again. By implementing this formula, you produce the P matrix. And then we're going to be analyzing our results. So as I mentioned in the last video, whenever we built our M matrix based on our full list information, this wasn't the proper way to build the matrix for multivariate regression. What we need to do is we need to add a 1 column to the end of our rows. So I've copied this particular cell, and I'm going to paste it in here. And what we're going to do is we're going to map each row, and we're going to take that row and we're going to add a 1 element onto the end. And then we're going to convert that to a matrix. Great. So now if we look at the matrix, it should be a 1,682 by 19 matrix instead of 18, where the last column represents all ones. So now we perform the multivariate regression, and we implement the formula that we saw in our slides. So I like to begin with the X transpose by X. So let's implement that. So the transpose of our M matrix and then the M matrix, and then we're going to multiply that. So there's the X transpose times X, which I have named M in this particular data set. Then we take the inverse matrices of that, and then we multiply that times the multiplication of the transpose of our matrix times our dependence. These two parts need to be multiplied together. Hopefully all of my braces have balance there, but there you go. There's our formula once again. I need to name this. There we go. So here are all of our coefficients. Now this is hard to sift through because every single row in this matrix represents one genre, except for the last one, and that's going to represent our y-intercept. So let me utilize a little bit of information from the beginning. Long SQL query here. I'm going to borrow from this one just for a second. Not for the purpose of analysis, but just for the purpose of understanding that matrix which we just made. I'm going to copy all of our genres. I'm going to scroll down here. Now if I type in words and I pass in all of our genre information there, what I've done is I've effectively split up all of the genres into a list. So I'm going to modify this line here. I'm going to zip all of my genres with a concat toList of my P matrix. And so that toList function is part of HMatrix that converts your matrix into a list of lists. And then I'm concatenating all those lists together, and I am zipping it up with all of the genres. And so what you'll see, every single genre matched up with its coefficient. And I'm going to add one more item to the end of westerns, and that is the intercept. And hopefully this will spill out just a little bit easier. Great. Now you can see each pair of items along with its coefficient. So I believe that this is a whole lot easier to visualize than this up here. For example, we see that anytime there's an action movie, well, users tend to subtract the rating score from that. And anytime people saw a war movie, people added 0.4 points to that. And all movies start out with a rating of 2.8, whether it's part of any genre. And you can see through here that westerns are liked, that increases the rating. War movies are liked, that increases the rating. Children movies are not appreciated. You'll see that there's a negative score there for children's movies. Action movies are not appreciated. There's a negative score there. You'll see fantasy movies, E -2. That means that is a very small number. And so even though that's a negative, I essentially treat that as a very small number close to 0. So fantasy movies have a negligible impact on ratings in our data set. So there you go. We see that the most appreciated genre, I believe, is film noir, and the least appreciated genre, children's movies. So there you go. We're going to be exploring the adjusted R-square in our next video. So there you go. In our next video,
how to compute the adjusted R-squared score of a multiple regression. In this video, we will be discussing how to compute the adjusted R-squared score of a multiple regression. So in this video, we're going to take a look at the steps necessary for computing the R-squared score. We're going to see that the R-squared score is insufficient for multiple regression, and so we have an alternate to that called the adjusted R-squared score, and we're going to be discussing the steps for that as well. We are going to compute the R and adjusted R-squared score on a multiple regression, and then we're going to discuss those results. So here's our motive. In the last video, we discussed how much of an impact each genre had on the enjoyment of a movie. So in this video, we're going to discuss a more important question, really. Can we trust the results of that regression from the last video? In other words, if I told you that a movie was a children's animated comedy and will be rated 3.06 out of 5, how confident will we be in that estimation? So think back to our discussion on linear regression. We had the R-squared correlation coefficient, which told us how two variables related to each other, and those variables were the independent variable and the dependent variable. Well, now we're talking about multiple regression, and we have multiple independent variables, but still just one dependent variable. It turns out that as more variables are added to our model, the R-squared correlation coefficient increases naturally for no other reason than there are more variables. And because of that, we have what's called the adjusted R-squared correlation coefficient, which is an attempt to offset that natural increase that we see in the unadjusted R-squared. So in computing the R-squared, we begin by finding the average of our dependent variable, and you see there the formula for the dependent. We then begin by computing the sum of squares of each dependent minus the average, and then we compute the sum of squares of each dependent minus the average. And you can see that in the lower bottom left-hand equation there on the screen. After that, we compute what's known as the sum of squares of each dependent minus the estimation of that results. And you can see that formula there in the bottom right-hand formula on your screen. Those formulas respectively are called the SYY and the SE. So once we have those two values, SYY and the SE, we can now compute the R-square. And it's simply 1 minus SE divided by SYY. That's the first formula you see on the screen. So in computing the R-squared and adjusted R-squared scores, we are going to begin with the R-square. We see the first formula there. It is simply 1 minus SE over SYY. In computing the adjusted R-squared score, we're going to need two additional pieces of information. First, we need N, which is the number of observations in our data set, and we need M, which is the number of independent variables. And once we have those pieces of information, we can compute the adjusted R-squared, which is 1 minus R squared times N minus 1 over N minus M minus 1. What we're going to do now is we're going to compute the R-squared and the adjusted R-squared score for our movie lens dataset and see if we can get worthwhile results. So I'm back in my notebook where I am performing multivariate regression, and I have added a line to my notebook called fill all. It's a function called fill all, and all it does is it takes a rows and a number of columns and a value, and then it creates a matrix where every row and column has the same value. So I can say fill all, let's give it 3 rows and 4 columns, and we'll say the number is 10 in each cell. And we've produced a 3x4 matrix where 10 is in every cell. We're going to use this in a few of the calculations that we're going to perform in this video. So let's begin by finding y bar, which is the average of our dependent variable. So we can say y bar, we'll say sum, and we'll take the head of the transpose of our D variable. So we're taking our D matrix, we are transposing it, we're grabbing the first, essentially the first column of that matrix, but since it's transposed, it's really the first row, and then we're computing the sum of that. And then after we've computed the sum, we're going to divide by the number of observations. We have 1,682 observations in our data set. And we see that we have a y bar of 3.07. So the average movie rating is 3.07. We need to compute the SYY. So let's say SYY. And this will be equal to every dependent minus the average. And we're going to use our fill all matrix in order to subtract each dependent from the average. So we're going to say TR of our dependent matrix minus, and we're going to fill all matrix with 1,682 rows and exactly 1 column, and each cell is going to be equal to our y bar. And we're going to multiply that by the exact same thing. So D minus fill all 1682 1 y bar. Great. Let's check out our SYY score. All right, so our SYY is 1027. We need to compute SE, which is the sum of squares of each dependent minus the estimation. So let's do SE, which is equal to mul divided by TR, and then we're going to compute our estimation on the fly, which is the M matrix times the P matrix, and then we'll immediately subtract the dependent. And then we'll do the multiplication of the M matrix and the P matrix again, minus the D. Great. So let's check out our SE score. So now that we have the SYY and the SE, we can now compute the R squared score. So that's going to be R squared, which is equal to 1 minus SE divided by SYY. Now this in itself is going to be a matrix, and so I am going to use the at index in order to take that matrix and immediately extract whatever is at index 0, 0. Now it's only going to be a 1 by 1 matrix anyway. Takes the value out of our 1 by 1 matrix. So let's check out what our R squared score is. All right, we got 8.8 times 10 to the negative 2. Now, if you recall from our discussion on R squareds from linear regression, an R squared of 0 means a very poor regression, and an R squared of 1 means a good regression. So this number is closer to 0 substantially than it is to 1. So what we have here is an untrustworthy regression. I would not feel confident about using this in any sort of non-instructional purpose. But since we are using this in an instructional manner, I think this is fine to explore a poor result. So we have a poor result. Now the whole purpose of discussing the adjusted R square is to take into account the natural growth of all of the variables that have gone into this calculation. Now we've had 18 independent variables that have gone into this R squared, and there's some natural biases that happen to the score. Our N is 1682, so I'm going to store that in a variable, and our M is equal to 18. I'm going to store that in a variable as well. And now we're going to compute the R squared adjusted, and it's 1 minus R squared times N minus 1 divided by N minus M minus 1. Let's check out what our adjusted R squared score is. So we have 7.89 times 10 to the negative 2. Notice that the score is going to be a little bit lower than our original R squared score. You're going to find out that this will always be the case. The adjusted R squared score will always be smaller than the original R squared score. And it's simply because we're trying to offset some of those balances. Now again, we have a poor result. And so this would not be good for a published result. Well, despite that, we can still learn from it. And we are going to explore how we can improve this adjusted R squared score in our next video. So our next video will be on improving the adjusted R squared score. In our last video, we calculated the adjusted R squared score for our multiple regression. We learned that it was a really low score, and we should never be evaluating the ratings of movies based on the genres of those movies. In this video, we're going to look at techniques for improving the adjusted R squared score. Now, even though we learned that movie ratings don't correspond at all to their evaluations, let's go ahead and walk through the steps on how we might improve an adjusted R squared score. So in this video, we're going to take a look at techniques for improving adjusted R squared. Perhaps you want to find better results, and in order to find better results, we use fewer variables. We're going to lay out a quick function for computing the adjusted R squared, and we're going to walk through the steps of improving our adjusted R squared score. So here's some tips for improving the adjusted R squared score, and they all boil down to using fewer independent variables. And there are three approaches which you should know about. The first of which is forward selection. And in this one, we take a single variable and we treat our data set as a one variable data set. And if it improves our regression, then we include it in our data set, and then we pick out another variable. and we test two variables, and we see if that improves our regression. Now, if we ever come across an additional variable that doesn't improve our regression, we simply look for another variable, and we only take variables that improve our regression. At some point, you're going to reach a point where none of the variables improve a regression, and at that point, you can just stop. The next approach is called backward elimination, and in this case, you start with all of the independent variables as part of your data set, and you work backwards. So you remove independent variables, hoping that that removal will improve the quality of your data set. If removing a variable doesn't, well then you just pick another variable to remove. And at some point you're going to reach a set of variables where removing none of them improves your data set. So you stop when you can no longer improve that adjusted R-squared. The third approach is called forward-backward stepwise selection. And in this approach, you have a data set with all of the variables, but only one has been removed, and you have none of the variables, but one has been added, and you sort of work from both angles, trying to find which combination of variables produces the best result. And that one's a little more complicated. The other approach to improving the adjusted R-squared score is simply ask an expert. Find them, ask them what variables are relevant to your problem, what variables aren't, and usually they can tell you. But experts are sometimes hard to find, so our algorithmic approaches tend to be what we use. Now I'm back in my multivariate regression notebook. I'm going to begin with laying out a quick function called adjusted R-squared. And what this function does is it goes through all of the steps necessary for performing a adjusted R-squared score from start to finish. And you'll notice it takes two matrices. There's our M matrix of independence, and there is our D matrix of the one dependent, and it produces the full calculation. So let's go ahead and explore how this works. So we're going to type in ADJRSQRD We get a value of 7.89 times 10 to the negative 2, which is the exact same value that we computed in the last video. So what I thought we might do is go through that backward elimination approach, where I said all of the variables are part of our data set, but we remove one variable for the purpose of our analysis. And what's nice is that we can index over all of the data set and build a matrix of the entire data set minus one column. And let's go ahead and do that. So we're going to map over the indices from 0 to 17, and those are our 18 columns in the data set. We never include that 18th column, which is the last column, because that's a matrix of ones. So we're going to treat that as variable n, and we are going to pass over and create a tuple where the first tuple is simply Rn, and the second value in the tuple is going to be our adjusted R-squared, where we're going to pass in an M and a D. Now the M is going to be stripped by one column, and in order to strip a column, you basically have to pass in the indices of all the columns you wish to keep. So I'm going to use the upside down question mark, and you'll notice I've got it hidden up here in the search bar, and that's just because I don't have an upside down question mark key on my keyboard. So I fetched that ahead of time and I put it in my search bar just so I could paste it here. And we're going to grab all of the variables before column n, and in this case that's going to be 0 up to n minus 1, and then we're going to add to that another list of everything that comes after column n. So that's n plus 1 all the way up to 18. And that is our list. So let's run this formula. And so what we have here is our indices from 0 to 17, and we see the numbers of each regression as if that particular column were missing. Now, it may be hard to find a number, but there might be a number in here that's larger than our 7.89. So what I'm going to do is I'm just going to copy this formula, and I am going to copy this number. And we're going to say that number less than the possible number that we wish to compute. So let's run this one. And now we have each index listed in true and false values. So we're looking through here and we're looking for anything that has a true associated with it. We got one. So 8 true. If we look at 8 in our earlier data set, that's 7.93, and that is larger than our 7.89. So what I'm going to do now is I'm going to take my adjusted R-squared calculator function, and I am going to grab my upside down question mark, and I am going to pass in a list of the indices I wish to keep. So that's 0, 1, 2, 3, 4, 5, 6, 7. I'm going to skip 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And good, we're there. And I get a value of 7.93 times 10 to the negative 2. That is our value reported up here in our number associated with 8. And it's higher than our original adjusted R squared. So if we drop the 8th column from our data set, we can improve our adjusted R squared. And what we can continue to do is to repeat this process where we keep siphoning off variables from our M matrix and hopefully get a better result. Hopefully you get the process from here. I'm going to leave this to you as an exercise to the viewer to see if you can improve this any. So let's go over our section review. In video 1, we formatted our dataset into two matrices, independence matrix and the dependent matrix. We explored the process of multiple regression in video 2. In video 3, we evaluated the accuracy of our regression. We found out that we've got a very untrustworthy dataset. But even though we had an untrustworthy dataset, I feel like this was a good dataset in order to explore the complexities of multiple regression. We examined ways to improve the adjusted R-squared score of our regression. In our next video series, we're going to take a change and we're going to move over to text analysis algorithms in Haskell. Section 4 will be devoted to text analysis problems. So in this section, we're going to be looking at preparing our text for the purposes of text analysis problems. We're going to be taking a data set and cleaning it up so that we can analyze it. We're going to be finding the set of n-grams for a data set. Once we have two sets of n-grams, we're going to be finding the cosine similarity of those data sets. We're going to see how there are applications for that. After that, we're going to move to a different problem known as the TF-IDF word score. Our first video in that area will just be an overview video. We'll explore the fundamentals of TF-IDF. And then, for our final video, we will be performing an application of the TF-IDF word score. So our first video is just about preparing our text for the purpose of data analysis. So in this video, we are going to be describing the data set which we are going to be using for the rest of the section. And our data set is the Federalist Papers. We're going to be cleaning that data set, and then we're going to be dividing that clean data set into words. So let's do a brief history of the Federalist Papers. So the Federalist Papers were a set of 85 essays written in the 18th century in the United States. And they were all written anonymously. Now, years after these documents were released, historians have gone back and figured out that there were actually 3 authors in the dataset: Alexander Hamilton, James Madison, and John Jay. Now, even though we know that these were the 3 authors of the dataset, we are fairly confident that we've narrowed down the authorship of 73 of these essays, and 12 of these essays we don't know who the authors are. Now, while this is a significant set of historical essays for the purposes of the United States history, really for our purposes, they are a fun data set for exploring data analysis problems. So just a little bit more about our data set. As I said, that these are 85 essays, and so accompanying this video will be a file called federalist.zip that will contain all 85 essays divided into 85 text files. The first essay will be called federalist01.txt, and the last essay will be federalist85.txt. Now, I prepared this data set, and the first line in every single data set will contain what we believe to be the author of that data set. And as I mentioned in the last slide, for 73 of these essays, we know the author. And for the remaining 12, the first line will simply say author unknown. So I'm back in my virtual machine. I have a notebook set up that I have named text analysis. You can see here that we have 4 inputs set up. I have data char, I have data list as L. You'll see that I've got an L there. I have data hashmap strict as HM, and I have text printf. Now you may be wondering why I'm using the as lines here. There are functions which are named the same across these 2 libraries, and we're going to be using both of these libraries in this section. And in order to make sure that those libraries are not confused, if it's from data list, it's called L, and if it's from hashmap, it's called HM. The next block I have here is a function called readFederalist, which goes into my data store. All of my files are in the data folder, and it picks out one file in that data store, and it reads the contents into a list of strings, where each string represents one line in our file. So let's begin with building our corpus of the text, and our corpus is going to be the set of all 85 documents. Good. Let's look at that first document in our data set. So our first document will be the head of the corpus. Let's look at the type of the document. It is a list of strings. Let's look at the head of the first. So our first essay was written by Alexander Hamilton. Let's get the rest of the document. So I'm going to call this rest. You'll see that we're using tail first in order to get everything after the first line of the document, and then we are using a function called unwords, which converts our listing of strings into a single string. So if I print out this value rest, you're going to get the entire first Federalist paper essay. To the people of the state of New York. All right, and then you can see the rest of the essay here. It's a rather long essay. Don't be concerned too much with the content. Be concerned with who wrote the content. So I'm going to hit this button over here that's going to compress that item. What we would like to do now is to start cleaning this document. So let's do lmap to lower rest. And what you're going to see here is that the document has now been converted where every character is lowercase. All right, to the people of the state of New York. You'll see that none of the words in our document are capitalized anymore. This is a common technique in data analysis. We don't care if a letter of the alphabet is capitalized or not. So this is just a preliminary step. What we would like to do now is to remove all of the punctuation from our document. So let's do a filter. So with this line, we are filtering out our string so that we are only keeping letters of the alphabet and spaces. All right. Now you'll see that our text is all lowercase. There is no punctuation. and the only thing we have that is not a letter of the alphabet are single space characters. And so we have a few instances in which we have a couple of spaces here, and there's a space at the beginning of our document. That's okay with what we're about to do next. What we need to do now is to take our filtered clean text and to break this up into words. And so I'm going to call this first words. And I'm going to use the words function, and I'm just going to paste everything we have left. So if we do first words, I now have a list of strings where every single item is a single word in our document. Great. This is where we're going to end the video. So our next video will be about finding the set of n-grams for our list of words. In this video, we will be finding the set of n-grams for our document. So in this video, we're going to take a look at describing what n-grams are. We're going to be demonstrating how to group n words in a document, and then we're going to be demonstrating how to find the set of our group of n words. So imagine we have a sentence that is simply, this is a sentence. The 1 grams of this is a sentence would simply be each word in a list. This is a sentence. The 2 grams would be each pairing of words that appear next to each other. So this is a in a sentence. In 3 grams, we have this is a and is a sentence. Notice that every time we group together n words and then we move forward and then we group together n words again. Next we have our 4 grams, which is simply, this is a sentence. Based on our knowledge of n-grams, let's see if we can discover the n-grams of our first words data set. So we need a function that will find a subsequence of words, and I'm going to call this sub-seq. So sub-seq takes really 3 arguments. This is a partial function. Let's look at the type of seq. So you'll see there that we have 3 arguments, an int and a list. So the first parameter start represents where we start the subsequence. The second parameter len represents the length of that subsequence, and then the third parameter is the sequence itself. And so we are going to drop the first starting values in the list and then take the length. So let's do a quick example. So the first 3 words in our document are to the people. To find the next subsequence of words in our list, we simply increment the start parameter by 1. To find the next sequence, we increment the start parameter by 1. Alright. So our document begins with to the people of the. And you can see the first 3 n-grams, where n is set to 3, of our document. So we're going to create a quick function, and I'm going to call this n-grams, that will go through an entire document and find these pairings. So this is going to take 2 arguments, the first of which is our list of words, and the second of which is going to be the size of our groupings. So notice that we are indexing through our list of words, starting at location 0 and ending at the number of words in our list minus n. This way, we don't have a grouping in our list with fewer than n words in it. Notice also that we are using the unwords function in order to take our sequence and to combine them into just a short list of words that exist in a single string. We're going to do a quick example of this function. We're going to do the 2 grams of our first words data set. So you can see how we have now combined into a single string each 2 grams. Now you'll notice that if you scan through this list, you're going to see a lot of repeated phrases such as to the, of new. Now I imagine that these are going to be repeated often throughout the document, and we really don't need these to be repeated in our document. We need to find what's called the set of our n-grams. So in order to find the set of our n-grams, we simply load these into a hash map. So there is where our hashmap function comes in. So I'm going to call this one map. One being that this is our first document. We're going to use the fold L inside of our list environment, and we're going to combine all of these into a hash map. So give me a moment while I type this out. Alright, let's explain this line. One map is now a hash map of all of our n-grams. You can see that we've computed the 2 n-grams of first words, and I am simply repeating that line here. That empty line there means that we are starting with an empty hash map, and I am passing each of our phrases into our empty hash map with insert width. And you can see that if a phrase does not exist in the hash map, it starts off with a value of 1.0, and if it does exist, we simply add to it with 1.0. So whenever I look at my one map here, you now have a hash map. And we can scan through this line, and you're going to see that each of our n-grams now has a number after it. Most of the time it's a 1, but you can see here the same. That appears twice in our document. Of government, that appears 4 times. And this is necessary for our next phase. We're going to stop here, and we're going to talk about our next phase, which is all about cosine similarity. In this video, we will discuss the cosine similarity of 2 datasets. So in this video, we're going to take a look at describing what cosine similarity is. We're going to be describing how to compute the cosine similarity of 2 maps in Haskell, and then we're going to be performing the cosine similarity on 2 maps and describe how it's useful. So imagine that we have 2 vectors, a and b. We can compute the dot product on a and b by finding the magnitude of a times the magnitude of b times the cosine between those 2 angles. Now it's the cosine that we need to focus on. We need to isolate that cosine. So the cosine is going to be the dot product of a and b divided by the magnitude of a times the magnitude of b. From there, we can apply the formulas of the dot product and the magnitude, and you see that there in the rest of the formula. What's interesting about this is that the similarity between 2 vectors is simply that cosine. And you don't even have to use the cosine trigonometric function in your environment. You simply solve that formula, and that produces the cosine of an angle. And if you recall, the cosine of an angle is on a range of -1 to 1, where if a value is 1, that means 2 vectors are identical. And if you have a cosine of -1, then 2 vectors are diametrically opposed. And if you have a cosine of 0, that means that 2 vectors are orthogonal to each other. So this one little quick measurement will tell us a lot about how 2 vectors are combined. And you'll notice it's on a range of -1 to 1. So I'm back in my notebook, and I have added a quick function to my notebook that summarizes everything that we did in the previous video. It's called doc2map. And with doc2map, it takes a document out of a corpus and performs all of the necessary operations in order to convert it to a map, such as cleaning the document, converting it to n-grams based on a size, and then converting it to a map of those documents. So let's get the one map of our document 1. So this is the one map of our first document, of course. Because in Haskell all lists begin at index 0, we say that 1 is at location 0. And this is the 2 n-grams of one map. I would like to do this again for 2 more maps. We're going to do 2map, which is the doc2map of our second document at location 1. And I would like to do the 6map. Now let's look at the head of 2 and 6. So if I say 2 is the second document in our corpus, I can look at the head of 2 and see that it was written by John Jay. And if I get the 6 from our corpus, I can look at the head of that, and we see that it is written by Alexander Hamilton. So if you recall that document 1 was written by Alexander Hamilton, document 6 was written by Alexander Hamilton, and document 2 is written by John Jay. In the context of author similarity, if I were to compute the similarity scores between the two Hamilton documents, I should get a higher score than if I were to compute the similarities between a Hamilton and a John Jay document. And let's see if we actually get that. So we're going to need a couple of functions in order to compute the cosine similarity. First, we need the sum of squares. And give me a moment, I'm going to type out this function. Good. Notice that this is not the sum of squares of a list, it's the sum of squares of a map, where we take the intersection of two vectors and then multiply that intersection, and then we compute the sum of the overall intersection. Next, we need the cosine similarity function, which you saw in our slides. Give me a moment, I'm just going to copy and paste it because it is a long formula. Here is our formula for the cosine similarity. Notice that it takes a hash map and returns a double. And we are computing the sum of squares between the hash maps of A and B. That's called SAB. And the sum of squares between A and A, that's SAA. And the sum of squares between B and B, and that's SBB. And now we have SAB divided by the square root of SAA times SBB, and that is our cosine similarity. So let's explore what the cosine similarity returns. As we discussed, it should always return a value from -1 to 1, where -1 represents diametrically opposed vectors, and +1 presents similar vectors. So let's compare our first document written by Alexander Hamilton and our sixth document also written by Alexander Hamilton. Good. So the cosine similarity score between our two documents, in which we are fairly certain were written by the same author, is 0.48. Now let's compare two documents in which we're fairly certain were written by different authors. Notice that we got 4.63, which was a slightly lower score. It's still very similar. I mean, it's still a good score, but it's slightly lower. Let's go ahead and compare 2 to 6. All right, this was our lowest score. So we are comparing a John Jay document to a Hamilton document, 0.41. So higher scores represent that it's more likely that the same author wrote both documents, whereas lower scores represent that probably different authors wrote those documents. Well, that concludes our discussion on author similarity. What you can now do with this knowledge is to explore the data set, find the documents that were written by an unknown author, and then try to figure out which of the other documents in the data set were written by the documents that we believe are unknown. Maybe you'll find something interesting out of that endeavor. Now we're going to move on to a slightly different topic in our next video, and that will be on what's known as TF-IDF word scores.
In this video, we will be providing an overview of the TF-IDF term frequency score. So in this video, we're going to take a look at reviewing the term frequency of a function. We're going to be reviewing the inverse document frequency function, and then we're going to be writing both of these functions in Haskell. So what is TF-IDF? TF-IDF is a weighting score to determine a term's importance to a document compared to that same term across a series of documents. So whenever we're looking at a term, we're trying to figure out if it's important to that particular document. And so if it's important to that particular document, it should be used multiple times in that document, but rarely used across other documents. Terms that are unimportant, such as a, and the, are going to be words that appear across all of our documents. So the weight of a single term in a single document is known as the term frequency. whereas the weight of a term across a series of documents, or what we call a corpus, is called the inverse document frequency. So the term frequency of a term is that term's impact on a document. And what we want to see are more occurrences to indicate a greater impact. And so we look at the number of times a term appears in a document, and we divide that by the maximum frequency of any term in that document. We multiply that value times 0.5, and we add 0.5 to it, and that becomes our term frequency score. The inverse document frequency of a term is how common or rare that term is across all documents in a corpus. Now, in order to have a greater impact in the inverse document frequency score is to be mentioned in as few documents as possible. To compute this, we find the total number of documents in our corpus, and then we divide by 1 plus the number of documents containing this term. And then we compute the log of this value. Now, the reason why we compute 1 plus the number of documents in the term is that if we find out the term doesn't exist at all, well, then we have a division by 0 problem. And so that's why we add the 1 plus there. Finally, we have the TF-IDF score, which is simply the term frequency times the inverse document frequency. So let's go ahead and write these functions. So I'm back in my Haskell library, So I'm back in my text analysis Haskell notebook. Let's write the term frequency function. It'll be named TF. You can see that I am using maximum on the largest element in my frequency map for the denominator. For the numerator, I'm using lookup, where the default score is 0. And then it's just a simple calculation. Now let's go ahead and present the inverse document frequency. Now this is a slightly more complicated formula, so I'm just going to paste it into the window. Notice here that I'm using generic length of our corpus maps. We'll discuss corpus maps in our next video, but it's simply all of our corpuses. And then I'm dividing that by 1 plus, and then I'm using filter, and I'm asking for each corpus map, does that term exist in the map using the function member? And then I'm finding the length of that list. Next, we need the TF-IDF function. It is simply the product of the TF score and the IDF score. We're going to end the video here, and we're going to pick up in our next video with a discussion of how we're going to use this with our data set. So in our next video, we are going to be applying the TF-IDF score. In this video, we will take our knowledge of TF-IDF scores that we learned about in the last video and apply them to our data set. So in this video, we're going to take a look at creating what we're going to call a corpus of maps. Now we already have our corpus, we just need to convert each document in our corpus into the hash map format. We'll be evaluating the TF-IDF score of a single term, and then we'll be evaluating the TF-IDF score for an entire document. So I'm back in my text analysis folder. I need to import one library that I forgot to import in video 1. So let me do that. Now we're going to need data traversable for our next activity in creating the corpus of maps. So now what traverse does is it's going to index through our doc2map function and grab each file and convert it to a hash map. So corpus maps is going to be a list of 85 hash maps. So what I would like to do now is to focus on one of Alexander Hamilton's documents. It's Federalist number 8. So we're going to call this the 8 map. So that's 7th in our list, so to get 8. And we need to make sure that our n-grams is set to 1. So in order to do TF-IDF, you really need to set the n-grams to be 1, so each element is its own word. Now, I mentioned that the TF score of a word represents the power of that word in the document. And there is no word in the English language that's more powerful than the word the. So let's look up the's TF score. You'll notice it has a score of 1, making it the most powerful word in this document. But you'll probably realize that the is not an interesting word. We really want better words in order to summarize this document. So let's look at the IDF score of the across our entire corpus. This command takes a little bit of time because it is going through the entire corpus looking for every occurrence of the word the. We get a very low score. In fact, it's negative. If you'll remember, the TF-IDF score of a term is simply the product of the TF times the IDF. So TF-IDF, and then we'll pass in the, and then we'll pass in our 8 map, corpus maps. Good. You see that we got a very low score for our term the. Now what I would like to do now is to compute the TF-IDF score of every word in our document 8 map. So you'll see with this command that I've just written, we are taking the keys of every term in 8 map, and then we're passing it into the TF-IDF function, and we're computing a score, and we're pairing it with the term itself. So if you were to print out this document, let's go ahead and print it out. This will fill up the screen with lots of data. And you see every single term in the document with its TF-IDF score. Now some of these terms are important and some of these terms are not important, and you can essentially rank this document based on the highest scores. In fact, I would like to go ahead and do this. Now I've already gone through this data set and I know that there is a set of terms that are quite interesting and they all have a score greater than 1.8. So I would like to do that. Alright, with this command we are looking for all of the terms in our document with a TF-IDF score, and you can basically call that term the important score, greater than 1.8. So we have exploits, supersede, retaken, protectors, degrades. And based on this word list, you can sort of get a feeling for the passion in Alexander Hamilton's writing. So this is a fun activity to look at, to try to look at the most important terms. And you're going to see that there are no boring terms in this list, no short, irrelevant words. So good. And this is the key benefit to the TF-IDF score ranking of terms. So in this section, we began our discussion on text analysis by cleaning up a raw data set, and we cleaned up the raw data set of the Federalist Papers. We then looked at the topic of n-grams, and n-grams are used in lots of contexts. In fact, we had 2 different contexts in this video series, the first of which was the cosine similarity between 2 documents. The cosine similarity between documents is used for things such as author similarity. We then went on to a discussion of TF-IDF, and it too requires the n-grams of a document. And we found the TF-IDF scores of all the most interesting words in Alexander Hamilton's Federalist number 8. So, in our next video series, we're going to start discussing clustering algorithms. In this section, we will be discussing clustering analysis, as well as introducing 2 algorithms for clustering data sets. So in this section, we're going to take a look at an intuitive discussion on clustering, as well as the essential terminology and some of the complications involved in clustering. We'll be introducing functions for the purposes of generating data for clustering. We will have a discussion on how to compute the distances between clusters. And then finally, we're going to introduce 2 algorithms for clustering data sets, and those 2 algorithms are k-means clustering and hierarchical clustering. So our first video is just a discussion on terms and issues related to clustering. So in this video, we're going to answer the questions regarding what does it mean to cluster, as well as what is a cluster. And then we're going to go through some examples of data sets in order to count the number of clusters, and we're going to see it's not always obvious. So first off, why do we cluster? So clustering is used to automate the process of lumping data together. As humans, we do this intuitively. In fact, it's hard for us not to automatically cluster. So examples of clustering in the real world would be sorting your garbage for recycling. That's clustering. Or sorting your laundry into lights and darks. That's clustering. So clustering is a method of exploring the structure behind data. Clustering should always be followed up with a second confirmation method because clustering is not always perfect. And in my view, clustering is a lot of fun. So let's try to answer the question about what is a cluster. So to begin, there is no clear definition of a cluster. Now, one of the essential terms regarding clustering is the term observation. So an observation is a record of values in our data set, and you can think of that as just being a row of data. So a cluster is a collection of observations that are all similar. Now, rather than thinking in terms of similar, you could say that a cluster is a collection of observations that differ from one another. Now, having said that clusters are either similar or different, you can define similar and different based on what your needs are. So here's a definition of clustering that I found in a textbook. Clusters exist in a continuous region of high point density separated by regions of lower point density. So this definition lacks rigor as well. At what point is a density considered high density versus low density? What I'm trying to get at here is the definition of a cluster is not always obvious, as we're going to see in a few examples. So study the image that you see on the screen and try to guess at how many clusters you see. In other words, how many groups of dots you see in the image. So in my mind, there are 3 clusters. There's a cluster in the top left corner, there is a cluster in the middle, and there's a cluster in the bottom right corner. Now I used a function which we are going to introduce in the next video to create this data set, and I told the algorithm to generate 3 clusters with sigmas 0.25, 0.5, and 0.75. Now when it comes to clustering, I consider this a happy case. You can see that there are 3 clusters, there are large gaps between the 3 clusters, and that means all 3 clusters are clearly separated. Not all datasets are this easy to work with. So study this image. How many clusters are in this image? Well, it turns out that this was generated using one random cluster. So this case demonstrates that clustering data doesn't always make sense. Since I generated this dataset using only one random cluster, technically there's only one cluster in this image, regardless of what else you see in this image. So clustering is not always obvious. So here's our final example. How many clusters are in this image? It turns out that there are 5 clusters in this image. So up in the upper left-hand corner of the image, you'll see that there is a collection of dots that tend to have more dots than some of the other groups that you see in the other corners. So there are actually 2 clusters in that upper left-hand corner. This is an example of clusters which overlap, which are hard to distinguish. So what is a cluster? So now that we've gone over a few examples of clustering, where you've had to count the number of clusters in each image, let's go over a new definition of clustering. A cluster is whatever definition best meets your needs of the problem which you are trying to solve. Now, more often than not, we gravitate to a geometric definition, which means we differentiate clusters based on their distance apart from each other. Now we're going to look at how we compute these distances in a future video. In our next video, we're going to introduce our function
for generating random data for the purposes of clustering.
In this video, we will be discussing how we are going to generate random data for the purposes of clustering. So in this video, we're going to take a look at a reposition function for feature scaling and moving around data. And that is necessary for creating clusters. And we're going to be using that function for our random clusters function, which will be introduced next. After that, we're going to be exploring some randomly generated data sets that will be used for our analysis of clusters for the remainder of the section. So let's go over to our Linux notebook. So I'm back in my Jupyter notebook. I have created a brand new notebook called clustering, and I have several libraries imported: system.random, data.list, data.maybe, data.org, graphics EasyPlot. These are all libraries that come standard in Jupyter, except for graphics EasyPlot. That one should have been installed from a previous video. What we're going to do is we're going to create our functions for the purposes of generating random data. So let's get our random number generator set up. We're going to name it G. Great. Now let's create a function called reposition. It's a long one, so I'm just going to paste it into the window. And what this function does is it takes a list of values, it takes a sigma, it takes a mean, and it will return our list of values that have been feature scaled to this particular sigma and mean. So it's been doing feature scaling and repositioning. So let's look at reposition. We're going to take the values 0 to, say, 20, and we're going to scale them to a 0.5 sigma with a mean of 0. All right, let's see what we get. So notice we get the values from negative 0.25 to 0.25. Now let's do this again. I'm going to take my line, and we're going to increase this to 1.0. Notice that my distribution of the line spread a little bit. We're at negative 0.5 to 0.5. We're still at mean 0. And let's do it again one more time. We're going to change that mean to be 1.0. Well, you'll notice here that all of my values have just had 1.0 added to them. We're now at 0.5 to 1.5. So hopefully you can see by reposition, we're taking any sequence of numbers, we're feature scaling them, we're multiplying them by a sigma, and then offsetting them by a particular mu score. Okay, our next function is going to be called random clusters. And I'm going to paste it into the window because it is another long one. So random clusters takes in lots of parameters, and it gives back a tuple of a list of values. This first value in the return are our x values, and the second value in the return are our y values. Well, I believe it would be best to describe what this algorithm is doing by using it. So first, let's generate some values. So values is 80 values taken at random from our random number generator. Let's look at those values. All right, so we got a lot of data here, just random numbers. What random clusters does is it takes this list of 80 values and it's going to divide these values into two groups, so 40 values each. We're going to have 40 x values and then we're going to have 40 y values. Then it's going to split those 40 values into various chunks where it's going to apply a x mean and a y mean to the data set, as well as multiply all values by a particular sigma. And so that is the listing of our parameters. You see the first values are values, the second list of doubles is our sigmas, our third list of doubles is our x mu's, and our fourth list of doubles is our y mu's. So let's create 4 clusters using this particular function and plot the results. So it's going to give back a list of x values and a list of y values. We're going to generate some random clusters based on our values. So you see that we're passing in our list of values into random clusters, and then we're passing in our list of sigmas. And we have 4 sigmas here, from very small to larger, so 0.25 to 1.0. And what this means is that you're going to spot 4 clusters of data in our data set, where one cluster is a very tight data set, and they'll slowly get more and more spread out. So the larger the sigma value, the more spread out your data set is. Now, the third sequence of numbers are going to be our x offset. So I'm going to say, so there's our x offset. We're going to say 1, 1, negative 1, negative 1. And then next we're going to do our y offsets. All right. Now, if you've ever taken an algebra course, you can see that the first x value is paired with the first y value. And so our first cluster is going to be at location 1, 1. And then you can see we're going in a clockwise fashion. So we're still at 1, but then negative 1. And then negative 1, negative 1, and then negative 1, 1. So it's going to be a U pattern that appears on the screen. So here's our x values. Here's our y values. Now let's see what this looks like whenever we visualize it. All right, there's our visualization. You can see the U pattern on the screen. So we start off with a very tight cluster. We have a larger sigma there. You can see the values are getting spread out. You can see our third cluster here in the U pattern. It's a little more spread out. And then we just have data that barely even resembles a cluster up here in the top left corner. Now there are 4 clusters in this data set because we set up our random cluster requirements with 4 values. And we're going to be performing cluster analysis on this particular data set. Now yours is going to look different from mine because your random number generator is different from mine. But there you go. And you can now play with random clusters in order to generate any number of clusters for your data sets. So in our next video, we will be computing the distances between clusters. In our last video, we used the random clusters tool in order to randomly generate a data set with 4 clusters. What we would like to do now is to learn how to compute the distances between clusters, because that's necessary in order to distinguish a point in one cluster from a point in a different cluster. So in this video, we're going to take a look at an overview of the 3 ways in which we can compute the distance between 2 clusters. We're going to introduce a function for computing the centroids of a data set, and then we're going to explore how to find the distance between 2 clusters based on what's known as the centroid. So imagine that we have a data set here, and I took our random clusters function and I generated a 2 cluster data set. Each of these clusters has 40 points in it, and I ask you, what is the distance between these 2 data sets? Now these data sets, blooper. Now these clusters are really amorphous clouds of data. They don't have a single concrete point to reference their distance between one cluster and the other cluster. But there are a number of ways in which we could make up a distance. One of these ways is we simply find the 2 closest points in our data set, and we say the distance between these 2 clusters is the closest point in our left data set and the closest point in our right data set. Now that works. It has a few issues, but it works. Now, another way of describing the distance between 2 clusters is by saying, let's go with the farthest points in a data set. So this way we look for the point in a data set which is farthest from another point in a data set, and we say that is the distance between the 2 clusters. Now, in my view, an easier way of
finding the distance between two clusters is by computing what's first known as the centroid. And the centroid is the average of a cluster. So we pick a point sort of in the middle of the cloud. It doesn't even really represent a point in the cloud. It is the centroid of a point. And we say that the distance between two clusters is the distance between their centroids. And this works fairly well. It's easy to compute, and it produces good clusters for most of our algorithms. So this is what we're going to use. Now, once you have determined the centroid of a data set, what you need to do is compute the distances between two centroids, and for that, we are going to be using a formula known as the squared Euclidean distance. So, in all three cases, we don't compute the pure distance. We compute what's known as the squared Euclidean, and that is known as the Euclidean distance, but we don't compute the square root that typically goes along with the Euclidean squared distance. So because all we're doing is we're comparing distances, without that square root, it really doesn't even change our calculation, so we just drop it out. And given a data set that all there is x and y components, we can use this formula and compute that squared Euclidean distance. So let's go over an example. So I'm back in my notebook. I'm going to drop a function into our data set that will compute our centroids. I've just dropped a function into our notebook which computes the centroids of a data set, and it's called getCentroids. So you'll notice it takes 3 arguments, a double, and then a list of ints. That first double is our x values, our second double is our y values, and then it's going to return a list consisting of the centroids of the data set, and then the third value you see there in the tuple is a label parameter. So in order to use this, you have to first cluster the data, or at least attempt to cluster the data. So what I'm going to do is I'm going to assume that we have 4 clusters in our data set that we used in the last video. So I'm just going to randomly apply a label to each of our data points that is either a 0, a 1, a 2, or a 3. So I have randomly generated a list of values where every value in that list is a 0, 1, 2, or 3. Let's look at this value. There you go. No consideration was made to make sure that one cluster was the same size of another cluster. There may be a small cluster in here. There may be a really large cluster in here. For our purposes, it really doesn't matter. We just need to come up with some labels for our data set, and we're going to pretend that this is a clustering of the data. We know it's wrong, but let's pretend that this is the starting point to our clusters. So let's generate some centroids. You'll see here that we have computed the centroids for each of our clusters. We believe that there are only 4 clusters in our data set, so our list is only 4 elements long. And all we're doing is we are focusing in on one cluster of data, and then we're going to average the x values and average the y values, and return a tuple of the average of those x and y values, along with the cluster label. So our cluster label for 1 is at this location, the x and the y. Our cluster label for 0 is at this location for the x and the y. Now let's compute the distance between our first and second points in our centroids. Good. So you can see that AX is going to be negative 0.26, and we have negative 0.26. Again, your list of values in your cluster analysis will be different because we started this video off with randomly generated data. So let's compute the Euclidean squared distance between these 2 clusters. Great. So we got a value for the distance between these 2 clusters. All right. We're going to use these measurements and we're going to introduce k-means clustering in the next video. So our next video is on k-means clustering. In our last video, we discussed how to find the centers, called the centroids, of a cluster, as well as finding the distances between two clusters based on those centroids. We're going to need to use that information in this video about performing k-means clustering. So in this video, we're going to take a look at an overview of k-means clustering. We're going to be introducing several functions for performing k-means clustering, and then we're going to be demonstrating how those functions are used. So the general approach to k-means clustering is we randomly assign a label to each observation. Now, what that means is that we are going to create these random clusters. Now, each cluster, which is randomly defined, is going to have a centroid that can be computed. We're going to compute the centroids of each of those clusters. We're going to find the closest centroid to each observation and then update its label. And then we're going to return to step 2 and recompute the centroids on each of those observations and their updated labels. So each time we go through this loop, the labels should progressively get better. If at any point we find that the labels no longer change, we're going to stop clustering and fall out of the loop. Let's go over to our notebook and begin. So I'm back in my clustering notebook. We're right where we left off. I'm going to drop in the first function for clustering. This is called find centroids. And what find centroids does is, given a list of centroids, that's the first argument, and an observation, a single observation, that is the second argument, it's going to return which centroid in our list best matches this observation based on shortest distance. And so you can see we are computing the Euclidean distance squared between any two observations. We are mapping over our list of centroids based on our distance squared with our observation. We're finding the minimum distance in that. We're finding the index position of that minimum distance. And then we are returning which centroid matches that distance. So that will simply find our nearest centroids. Now I need to drop in another function. So our second function is called k-means. Now k-means is going to perform one loop of our k-means clustering. You'll notice that k-means takes a list of doubles, those are our x values. It takes a second list of doubles, those are our y values, and then it takes a list of labels, and it will return a new list of labels. So let's demonstrate how this works. We are going to perform one loop of k-means clustering using our randomly assigned data. So here is our list of random cluster labels that we generated in the last video series. So let's demonstrate what happens whenever we perform one iteration of k-means clustering. So we're going to pass in our xs, our ys, and our cs. And you'll see that it's trying to cluster our data. Now, one of the things that I didn't tell you about the clustering data function that we introduced in our second video was that each of the clusters are going to be listed in sequential groups. And because we have 4 clusters of 10 points each, the first 10 will represent the first cluster, the second 10 will represent the second cluster, the third 10 will represent the third cluster, and the fourth 10 will represent the fourth cluster. So you can see right off the bat, it looks like it found a cluster in the first 10 elements as well as a cluster in the second 10 elements very quickly after just one pass of our algorithm. But we're still trying to differentiate those third and fourth clusters in our list. So we're going to introduce our third function. So our third function that we are introducing is called k-means clustering. And you'll notice that the arguments for k-means clustering and the output are identical to k-means. And this will repeatedly pass in our cs variable to k-means, thus generating cs prime, and compare it with our original set of labels. And if they're the same, it will stop the algorithm. And if not, it will recursively call this algorithm on the cs prime.
So let's see what happens whenever we perform the recursive k-means clustering algorithm. Notice it requires the exact same arguments. And look at that. Notice after one pass up here that some of the clusters weren't defined. We only found 2 values in a single cluster. But after several iterations, it found all of our clusters. Now, let's say that you ran this algorithm on your computer. Your randomly generated data will be different than my randomly generated, and perhaps you didn't get the same results I did. If you didn't, that's okay. What you should do is try generating another CS list, and perhaps you can try with a different set of centroids. K-means clustering is known to fail at times, so this is not going to be a always perfect, accurate clustering mechanism. But knowing that, you can get good results with k-means clustering. In our next video, we will be performing hierarchical clustering. In this video, we are going to discuss our second and final clustering algorithm, hierarchical clustering. So in this video, we're going to take a look at an overview of hierarchical clustering. We're going to introduce several functions for the purposes of performing hierarchical clustering, and then we're going to demonstrate how those functions are used. So if you recall with our discussion on k-means clustering, each cluster in k-means clustering began with a randomly assigned cluster based on how many clusters we thought there were. And we even really believe that those clusters were accurate, but they helped us towards getting accurate clusters. Now in hierarchical clustering, we do something slightly different. Every single observation begins with a unique cluster. We treat each point as its own cluster. We then compute the pairwise distances between each cluster. We're going to find which two clusters are closest together and merge those by updating the labels of one to match the other. We're then going to return to step 2 with our new set of clusters, or we're going to stop if we believe that the number of clusters has reached our desired number. So let's go over to our notebook and explore hierarchical clustering. We're going to introduce our first function for hierarchical clustering, and it's called closest centroids. And you can see the function here. It takes a list of centroids based on a double and a cluster, and then it's going to return a double, and this is going to represent the distance between two clusters as well as the labels of each cluster. Notice that we are filtering out all of the clusters that have a distance of 0, and we're only keeping the clusters with at least a positive distance, and we are using those in order to figure out which two are the closest. Let's explore how this function works. We're going to get some centroids from our clusters. Notice how we're passing in for our list of labels 0 to 39. That way, each observation gets its own unique cluster label. Let's look at this list. You can see that there are 40 points in this list, comprising of triples with an X, Y, and a label in each triple. Let's find which of these triples are closest together. It looks like labels 23 and 25 are closest together. The next function that we are going to introduce is going to be merge closest centroids. So you'll see that in merge closest centroids, we are calling closest centroids, which we just defined. We are passing in a list of centroids, and we're passing in a list of labels of those centroids. And then we are indexing through our list of labels, and we are going to return a new list of labels, which will be updated. So let's demonstrate what happens whenever this algorithm is called once. So I'm going to call merge closest centroids on our list of centroids, and I'm going to pass in my 0 to 39. Now we knew from closest centroids that labels 23 and 25 are the closest. So you'll see in our new list of centroids, we have 21, 22, 23, 24, and then 23 again. What this function does is it finds all of the labels of whatever numeric was larger and changes them to whatever numeric is smaller. What we're going to end up doing is we're going to be using this as the input for future calls to merge closest centroids. And we are simply going to perform this repeatedly until we get the number of clusters down in our list of labels until we get a number that we like. Now we believe that there are 4 clusters in our set of XY data, so we're going to set our desired number of clusters to be 4. Now let me go get our proximity clustering algorithm. So this algorithm is going to be performing the hierarchical clustering. Notice it has some similarities to the algorithm which we worked on in the last video series. There are 2 conditions which I am setting for us stopping the algorithm. If we reach the desired number of clusters, in other words, if we unique our list with nub and the length is equal to 4, we're going to stop. Or if it turns out the labels produced by merge closest clusters aren't changing from the loop before that, we're going to stop our list. Otherwise, we're going to call proximity clusters on our new list of data. Because this algorithm doesn't rely on randomly assigned labels, this algorithm does tend to be a bit more reliable. And in fact, I like the results produced by this particular approach on more difficult clustering data than I do the k-means clustering. So let's see if this algorithm works with our XY data. So there's our original X, our original Y. We have our values 0 to 39, and we're going to pass in our desired number of clusters, 4. Now it didn't assign the exact same labels as our k-means clustering, but you can see that each group of labels is unique. The first 10 are 0, the second 10 are 10, the third 10 are 20, and the fourth 10 are 30. So it perfectly and accurately clustered our data based on a hierarchical structure to the data, where we slowly merged the 2 closest centroids together progressively. That, in a nutshell, is hierarchical clustering. It's time for our section review. We began with a discussion on what is clustering and how difficult it is to define a cluster. We created a simple function for generating data which can be clustered. I hope that you will use that function that we introduced in video 2 to create other clusters and to explore other types of data. I hope you will use that function for generating more data sets, and hopefully you'll discover how some data sets are more difficult to cluster than others. We had a discussion on how we compute the distances between clusters. Now the approach that we use in this particular video series is based on the centroids of clusters. We introduced our first full clustering algorithm, and that was k-means clustering. This is generally considered to be the hello world of clustering algorithms. We then followed that up with a discussion of hierarchical clustering in video 5. I tend to use hierarchical clustering in my clustering of data sets because I like the results and I also like that it's deterministic. In our next video series, we will be discussing Naïve Bayesian Classification. In this section, we will be discussing Naïve Bayesian Classification for the purposes of labeling documents. So in this section, we're going to take a look at a simple problem to illustrate Naïve Bayesian Classification. We're going to be writing a little bit of code to perform this classification, and then we're going to be applying that code to the Enron email dataset for the purposes of spam detection. So in this video, we're just going to have a discussion on Bayes' theorem and a sample problem in order to help illustrate the potential of Bayes' theorem. So in this video, we're going to take a look at what sort of problems that can be solved with Naïve Bayes classification. We're going to go over a sample problem involving candy from one of 2 possible candy jars, and then we're going to be explaining the parts of Bayes' formula. So suppose that you have 2 friends of yours, one of whom is a politician, and another of whom is an athlete. And
one of the two of your friends sends you an email, and it's your job to figure out which of your two friends sent you that email. So, naive Bayes classification attempts to assign a probability to an event, such as receiving an email, based on the existing known probabilities. For example, we're trying to write a document classifier to figure out which friend sent us this email. So consider the words scored, goal, and ran. If you were to see these words in an email, you might presume that they were about a sporting event. The player ran down the field, kicked the ball, and scored a goal. We would assume that our athletic friend sent us this email. So consider the words election, vote, and ran. Conceptually, these words might be found in a story about a political campaign. The candidate ran for office and told the people to vote in an election. So you can see that both of our sample sentences contained words that were similar and words that were different. So here I have lined up 5 words that were found in our sample sentence that I would consider sports terms, and then I have 5 words lined up from our political sentence that I might define as election terms. So a word, whether it has a meaning or not associated with a class, will contribute to that class. And in fact, a word contribute to both classes or other classes. So scored, gold, ran, and the. These are all words that are now sports terms, whereas election, vote, ran, and the, these are now election terms. You'll notice that the term ran has a real meaning in both sports and elections, whereas and the are considered stop words. They don't have a meaning outside of the sentences in which they are used, and these words are often removed in analysis. So here's our example problem in order to illustrate the parts of naive Bayes classification. So imagine that you have 2 cookie jars, one of which is going to be called jar A and the other is jar B. But you just see them sitting on a shelf and you don't know which one's which. Jar A contains 8 chocolate candies and 2 jelly beans, whereas B contains 5 chocolate candies and 5 jelly beans. All told, there are 20 candies across the 2 jars. Now let's say that I take a jar off a shelf and I hand it to you, and you reach inside and you pull out a chocolate candy. You aren't allowed to look at the other candies inside the jar. What is the probability that you pulled a candy from jar A? We're going to explore this in more detail. So let's look at the other aspects of the problem. So what is the probability of selecting a chocolate candy? Well, we know jar A has 8 chocolates and jar B has 5 chocolates. 8 plus 5 is 13. We know jar A has 10 candies total and jar B has 10 candies total. 10 and 10 is 20. 13 divided by 20 is 0.65, or 65%. So what is the probability that I randomly handed you jar A? Well, there's only 2 jars. There's a 50-50 chance of getting jar A, so the probability is 0.5. Now what is the probability of being given a chocolate? If I tell you you have been handed jar A, well, there's only 8 chocolate candies in jar A, so the probability is 0.8. I want you to notice how the formula is written. We say P chocolate bar jar A. That means the probability of chocolate given A. So A is assumed to be true. What is the probability of chocolate? Likewise, what is the probability of chocolate given jar B? Well, there's 5 chocolates in jar B, thus there's a probability of 0.5. So whenever we're asking if 2 events are true, in other words, what is the probability of a chocolate and jar A, we're asking for what's known as the conjoint probability. What we're really asking is, what is the probability that A is true and B is true, but we also know A is true? For that second part, if A isn't true, well, then the probability is 0. So what is the probability if A is true and B is true given that A is true? And we can write that out. The probability of A and B is equal to the probability of A times the probability of B given A. So let's put this into perspective of our chocolates. So the probability of jar A and a chocolate is the probability of jar A times the probability of chocolate given jar A. And that's 0.5 times 0.8, which is 0.4. What is the probability of jar B and a chocolate? Well, jar B is 0.5, a chocolate from jar B is 0.5, thus the overall probability is 0.25. Now let's add those two probabilities together. Now what is the probability of jar A and a chocolate, or jar B and a chocolate? Well, really that just boils down to the probability of a chocolate, and thus we have 0.65. It's the sum of those two probabilities. That's the same result that we got on the last slide. So let's look closer at our conjoint probability. So the probability of A and B is the probability of A times the probability of B given A. And the probability of B and A is the probability of B times the probability of A given B. You'll notice that those are equal. So the probability of A times the probability of B given A is equal to the probability of B times the probability of A given B. Now with a little bit of algebra, we can take that probability of A and move it to the right-hand side of our equation. We just divide both sides by the probability of A. So then we are given Bayes' theorem. The probability of B given A is equal to the probability of B times the probability of A given B divided by the probability of A. Now let's go back to our original problem of which jar did we get off the shelf given that we were given a chocolate. So we know that the probability of a jar is 0.5. We know that the probability of a chocolate is 0.65. We know that the probability of a jar given A is 0.8. We now have all the parts and Bayes' theorem in order to solve our problem. So the probability of jar A given a chocolate is 0.5 times 0.8 divided by 0.65, which comes out to approximately 0.62. Likewise, the probability of jar B given a chocolate will be about 0.38. Thus for a total probability of 1. Now, because 0.62 is greater than 0.38, we will assume that we were given jar A. So in this video, we've looked at Bayes' theorem, and we're going to use this Bayes' theorem in order to create a document classifier for our dataset that we'll be using for the rest of our section. In this video, we are going to discuss the code behind Bayes' theorem. So in this video, we're going to take a look at describing the Enron email dataset. We're going to be describing the specially made version of this dataset for this video series that I made personally. We're going to be performing the naive Bayes classification on one word in this dataset, and that word is website. So think back to our candy jar problem. We had two candy jars. Each jar had a mixture of chocolates and jelly beans. You were handed a jar, reached in, found a chocolate, and told to guess which jar you were holding. We guessed jar A because jar A had a higher probability than jar B. So in a very similar context, we are given a single word. You can think of this as a single candy, and that word is website. And we are told to guess who sent this, a coworker or a spammer. Now the Enron dataset that we're exploring has already been divided into two parts, called ham and spam. Ham represents the set of emails related to the Enron company, whereas spam represents the set of emails that are unrelated to the Enron. Now, the original dataset that I found online was comprised of 5,000 emails and their raw text. And what I'm providing is a SQLite 3 database. This SQLite 3 database is comprised of two tables. The first of which is the document table, where each row in the document table represents one file in the Enron dataset. In the word table, each element represents a word found in a document, along with the word itself and the frequency. Now in document, we have the document ID, which is a primary key, and in Word, we have a document ID, which is a foreign key, which maps to the respective document in the document table. Now, let's go explore our data set. So I'm back in my Jupyter notebook. I've got a few libraries imported ready here. I've got data.traversal and a few database-related libraries. And I've got a connection to the Enron SQLite 3 database will accompany this video series. So let's begin by counting the number of documents in this dataset. So we have 5,172 emails in this data set. Let's begin by finding the probability of our word, website. So in order to figure out the probability of a word, we need to know the total count of all words. So we have just over 850,000 words in our data set. Now you'll notice that I used the function total here as opposed to the more often used sum. And the reason is, total will always produce a numerical value, whereas sum will produce a null if no items are found. And because we're doing calculations, I really want a value returned under all circumstances. Next, we need to know the total number of times website is found in our data set. So I'm going to copy and paste my query, and I'm going to add to the end of it where word is equal to website. So website appears across the entire data set 139 times. So what is the probability of a word? P website is equal to 139 divided by 850,027. So it looks like the probability of finding the word website randomly is going to be 1.6 times 10 to the negative 4. It's a really small number, but that's okay. We're going to use that as part of our calculation. Next, let's calculate the probability of the word website given a label of ham. I'm going to take my query here, and we're going to build on this query. So because the label information is stored in the document table, but the word information is stored in the word table, we're going to have to combine our two tables. So I'm going to say word, comma, document. We're looking for the website, and we're looking for where word document ID is equal to document ID, and where the label is equal to ham. I realize it's a long query, and I hope I typed that up correctly. So the total frequency of finding website in ham is 74 times. Now let's figure out the total number of words in the ham data set. From here, we can just eliminate word website. The total number of words in the ham data set are 582,000. So let's figure out the probability of seeing website in the ham portion, given that it's ham. So we'll say P website given ham. And we'll say that's 74 divided by 582265. All right, so what's the probability of the website? So we have 1.2 times 10 to the negative 4. Again, it's a really small number. Now let's figure out the probability of a label. In other words, you are randomly given an email. Is it ham or spam? But you haven't looked at it yet. So we already know the total number of documents in our data set. That's 5,172. We're going to use that in this next calculation. In fact, I'm just going to grab this query and use it. So let's count the number of ham documents. So we have 3,672. So the probability of ham is going to be 3,672 divided by, and I'm going to scroll up just to check my number one more time, 5,172. And we see that the probability of ham is about 71%. We now have all the parts in order to perform the Bayes classification. So we're going to say, what is the probability of ham given website? And that is the probability of ham times the probability of website given ham divided by the probability of website. And so the probability of ham given the word website is 0.55, or about 55%. So if you have a letter and that letter contains the word website and you haven't looked at any other words, with a 55% probability, you can say that that is a company-related ham email. And likewise, it's about 45-ish%, a little under that, in order to determine that it is a spam email. And you can perform the calculation and you'll see that calculation be resolved. Now in our next video, we are going to create the calculation that performs Bayesian classification for every word in a data set. And we'll be showing off those functions. So in our next video, Naïve Bayesian Classification of full documents. In this video, we will be performing naive Bayes classification on full documents. So in this video, we're going to be introducing a quick function to perform Bayes on a single word. And then we're going to be using that function that performs Bayes on a single word and using it to perform Bayes on a single document. And then we're going to be testing out that function on a single document in our dataset. So let's take a closer look at the Bayes theorem one more time. So as we've seen in our past two videos, Bayes theorem is the probability of B given A, which is equal to the probability of A given B divided by the probability. So in this context, B is a label such as ham or spam, and A is a word such as website. And let's explore these three parts one more time. So when testing many words in a document, there's a few considerations. The probability of a word is the same regardless of the label being tested, and thus it's ultimately unnecessary for our calculation. It'll produce a different probability, but whenever we're comparing probabilities, so the probability of a word is the same regardless of the label being tested, and ultimately it's unnecessary for our calculation. The probability of a label is the same for every word, which means we only have to calculate it once. And the probability of a word given a label is the only real unique calculation that has to be done. So with this knowledge, we can optimize our Bayes theorem a little bit. So to perform the naive Bayes classification calculation for a label in a document, we're going to use this modified formula. So the probability of a label given a word will be equal to the probability of a label times the combined product of every word given that label. Once we have performed this calculation for all documents, we pick the label with the largest calculated value. So I'm back in my notebook. We're going to be evaluating one document in our data set to determine if it's ham or spam. And the document I've picked out is document number 8. So let's explore how document 8 is already labeled. We see that document 8 by default is labeled as a spam. And this was determined by the researchers who put together the original data set. Let's look at all of the words in this data set. So here you can see all of the words in document 8 of our data set. And now we are going to introduce the function, which is called Bayes word label, and we're going to explain the parts of this. There are three arguments to Bayes word label. There is a connection, which is going to be our database connection. There is the word which we are searching for, and there is a label which we are passing in. And then it's going to return probability of the word given the label for that word. And you'll notice right here, if the word doesn't exist in our data set, we're going to return a very small value, 0.00001. It just needs to be a very small value. So let's explore the probability of the word website given that it's ham. So here we see the probability of the word website given that it's ham. In fact, we did this same calculation in the last video. Now let's look up the probability of the word website given that it's spam. I'll just change ham to spam. And you'll see that a different probability emerges. Now these probabilities aren't comparable because they're from two different data sets. What we have to do is we have to scale them based on the size of each data set. So there was a 29% chance of having spam message, so 0.29 times our probability of spam. So this is 0.29, the probability of spam, times the probability of the word website given that it's spam. We see that it's 7.0 times 10 to the negative 5. And the probability of a ham email, which is 0.71, our probability of the word website given that it's ham, we see that it's 9 times 10 to the negative 5. Now these are really small numbers, but you can see that the ham calculation was marginally larger than the spam calculation. So we didn't even really need the probability of the word website. We could still gain that there was a higher probability for ham over spam using just this information. Next, we're going to introduce our Bayes document label. And what this function will do is that it will return a calculation for a document given a label. You'll see here that once again there are 3 parameters to our function, the first of which is a connection, the second of which is a document. Notice that it's a string, and the reason why it's a string is that attaching that directly to an SQL query. And the third parameter is the label which we are trying to discern. Now we have our email number 8, and according to the original source, we believe it's a spam. Let's see what our calculations have to say. Now, notice that all it's doing is performing those essential calculations that we discussed in the last video. But we're using the modified formula where we take the probability of the label times the combined product of all of our probabilities that come from Bayes' word label. And that is the essence of the function right here. Everything else you see is just gathering data for this essential calculation. So let's look up Bayes' document label, ham. Now this is a slow calculation. It's going to take my computer probably a few minutes in order to perform this calculation. And we're just going to sit here and wait. Now, through the magic of editing, we're going to skip straight to the very end. But on your computer, this will take a while. There we go. So we got a very small value, 4 times 10 to the negative 223. Now this value, 4 times 10 to the negative 223, is a meaningless value unless you have another value to compare to it. And we have a potential value that we can compare to it. We're going to look up the classification of our document based on spam. Once again, this is going to be a lengthy calculation, and with the magic of editing, we're just going to skip straight to the very end. So the spam result was 5 times 10 to the negative 198. Now these are incredibly small values, and in and of themselves, the values are meaningless. But once you compare the values across several labels, you can find whatever label produces the highest result and associate your email with that highest value. So because 5 times 10 to the negative 198 is higher than 4 times 10 to the negative 223, we are going to apply a label of spam to our email. And that's ultimately how to perform Naïve Bayes classification across a full document, multiple labels. So in this section, we step through a simple problem involving Naïve Bayes theorem. We explored a real-world dataset and performed Bayes on a single word. The single word was website, and our dataset was a sampling of 5,000 Enron emails. And then we explored how we might perform Naïve Bayes classification on a full document. In our next video, we are going to be exploring principal component analysis. In section 7 of our video series, we will be building a recommendation engine using the approach known as principal component analysis. So in this section, we're going to take a look at a discussion of the applications of principal component analysis. We're going to be creating the covariance matrix of a data set, and that is the necessary first step for PCA. The next step for PCA is eigendecomposition process, by which we generate the eigenvalues and eigenvectors of that covariance matrix. We're going to be finishing off the PCA procedure using dimensionality reduction, by which we use those eigenvalues and eigenvectors, and we take our original data set and we make it significantly smaller. And then we're going to be using the results of that dimensionality reduction in order to create the recommendation engine for our problem. Now I know that sounds like a lot, but we're going to go through it in lots of little steps. So our first video is strictly a discussion on PCA and the mathematics behind it. So in this video, we're going to be discussing the problem that we wish to solve, and that is movie recommendations. We're going to be exploring the useful properties behind eigenvalues and eigenvectors, and then we're going to be explaining the math behind PCA. So it's movie night, and you've come home from a long day of work, and you want to watch a new original movie that you know you're going to love, and you don't have any real movie in mind, but you wish that someone would make a recommendation for you. So if everyone liked the same movies, this would be really easy. We would just look in a database, find a movie that you haven't seen that's really popular, and just recommend it to you. But as we've seen on our section on multiple linear regression, it's not. So here's our problem. Everyone is different, and we all like different things.
So solution is to find someone like us and to see what we haven't seen from what they have seen and have liked. This in itself is its own problem. So the procedure that we are going to use in order to solve this problem is known as principal component analysis. And the problem that we're trying to solve is that there's a lot of data out there, and our data suffers from a problem known as the curse of dimensionality. Our movie data set has 943 users, each with 1,682 dimensions. That's one movie per user. While it's possible to compare a user to every other user based on all 1,682 dimensions in our data set, this process can be reduced to something far easier. So principal component analysis is the process by which we take a high-dimensional data set and reduce it into something smaller while keeping most of the relevant data. At the heart of principal component analysis is a procedure known as eigendecomposition. So eigendecomposition is the process by which we discover the eigenvalues and eigenvectors of a matrix. Now there are some interesting properties in these eigenvalues and eigenvectors. Eigenvectors point in the direction of skewness. A vector will always point. And so an eigenvector discovered by this process points in the direction of how a data is skewed. In other words, where a data is actually interesting. And the eigenvalues associated with those eigenvectors are going to report the strength of that skewness. And so while all eigenvectors point in the direction in which data is interesting, some vectors are going to be more interesting than others, and those more interesting eigenvectors will have higher eigenvalues. And so you can rank a vector based on its associated value. So here are the parts of our formula which we are trying to satisfy. Matrix A is a matrix which we are trying to discover the eigenvalues and eigenvectors. V represents a discovered vector, and lambda represents a eigenvalue, and it's just a single value, and it's going to represent the strength of the skewness of the data, whereas a vector represents the direction of that skewness. Now this tends to be a very difficult problem to solve, and we are not going to go through the algorithm for solving it. We're just going to introduce the function inside of our HMatrix library, which will solve this for us. Now a few essential things that you need to remember about eigendecomposition. Matrix A must always be a square matrix. Now there can be many solutions to this equation. In other words, what will be produced are many eigenvectors and many associated eigenvalues. But there will never be more than n solutions, where n is the length of one dimension of our square matrix A. If matrix A is a symmetric matrix, there's an interesting feature that arises. All of the eigenvectors will be orthogonal to each other. Now it just so happens that in the PCA approach, which we are using in this video series, matrix A will always be symmetric. Thus you can always be sure that all of the eigenvectors will be orthogonal to each other. Now the eigenvector that is associated with the largest eigenvalue will happen to represent the direction of the greatest amount of skew. Likewise, the eigenvector associated with the smallest eigenvalue represents the least amount of skew. And so it's good to remember that large eigenvalues are associated with the largest amounts of skew. Conveniently, the eigendecomposition process that HMatrix provides for us, and we will be using in this series, will automatically rank our eigenvectors based on eigenvalues. So here is the procedure for principal component analysis, which we will take for the rest of this video series. We're going to combine steps 1 and 2 in our next video, and that is we're going to prepare our data set and we're going to find the covariance matrix of our movie data set. In video 3, we will be performing the eigendecomposition of our covariance matrix. In video 4, we will be examining the top n eigenvalues, and we're going to be reducing our data set to that many columns. And you're going to find that n is going to be a far smaller number than 1,682. And we'll be exploring how to discover a good value of n. And then in our 5th video, we're going to be using that reduced data set in order to create a recommendation engine for one person in our database. So in our next video, we're going to be preparing our data set and finding our covariance matrix. In this video, we are going to be preparing our data set for principal component analysis, and we're going to perform that next step for PCA, which is to compute the covariance of our data set. So there's no easy way in order to prepare our data set without several SQL queries. We're going to be introducing a few SQL tables for the purposes of preparing our data set. We're going to be executing one final SQL query which will build our data set into a matrix M, and then we're going to be finding the covariance of that matrix M data set. So right now what we have in our data table in our MovieLens data set is 100,000 records of users and movies and the ratings assigned to those movies. Now if we were to convert this into a matrix with all of our users and all of our movies, we'll find that there's a lot of gaps in our table. Everywhere where there is a gap, we need to replace that gap with a value of 0. And so you can see here the final product which we are trying to create, where all of the movies are along one dimension and all of our users are along another dimension. So let's create our SQL queries and build our giant 1.5 million record matrix. So I'm back in my terminal, and what I need to do is I need to modify my movie data set with more additional tables. So SQLite 3, movies SQLite 3. All right, so if you recall, we have, I'm just going to remind you that in our select count from data, we have 100,000 records, and this represents our movies and our users' ratings for those movies. So let's create a table called numbers. This table, numbers, is going to have two columns, one of which is relevant and one of which is not relevant, but we still need it just for the purposes of building the table. So the ID integer primary key is going to be our relevant. It's just going to be a list of numbers. And our second column, word text, is actually irrelevant. We're not even going to use that column apart from our next step. So now we need to populate our table numbers with numbers. So this command is going to populate numbers with 100,000 rows, just so that we have an ID in each column with an incremental number all the way up to 100,000. I can select from numbers, and you can see that the ID field just increments 1, 2, 3, 4, 5, all the way up to 100,000. Using this, I need to create a view that is comprised of our user ID values, which is going to be a number from 1 to 943, and our movie ID values, which is going to be comprised of a number from 1 to 1682. Now, I hope I've typed in this view correctly. I'm going to try to explain it. We're creating a two-column number view where the first column is going to represent our user IDs from 1 to 943, and our second column is going to be a repetition of item ID from 1 to 1682. All right, that looks like it worked. So I'm going to select on this number view. You can see that there are 1.5 million records in number view, which are just incremental numbers from 1 to 943 and from 1 to 1682. And we're going to use this in order to build our 1.5 million record table. So let's go over to our notebook. So you can see that I've got my PCA notebook here. I've got data.list. I've got our database library calls, and I've got our HMatrix calls. And I need to restart and rerun all on our data set because our data set has been updated. I'm going to come over here and I'm going to exit out of this file, and now I'm going to come back and I'm going to do this one more time just to make sure that the proper database is loaded. Now let's build our results query. This is going to be what's known as a left outer join on our number view view and our data table. Now, as you recall, there is no data for a user and a particular movie, then we're just going to get a null from the database. So this is why I have here, if null, change that to a 0. So there is our left outer join between number view and data. And we're going to align these two tables. So where these two tables have aligned will represent somewhere in our data table. And if it's null, it's just going to get replaced with 0. And if there's an actual value there, then we're going to get the rating. Hopefully I've typed this correctly. Oh, let's see where I messed up. I misspelled number view. Alright, so we're going to fix that one very quickly. It looks like I typed it incorrectly twice. It looks like it worked. Now let's get the length of our results. It's building the query and getting our results now. So this is going to take a second. It's a rather large query. You can see that we have 1.5 million results. We need to parse these results into doubles. So I'm going to call this our values. I'm going to map it from SQL. We're going to transpose our data set. We're going to grab the first row, as you've seen us do several times before in past videos. And then we're going to take that list and convert it to a list of doubles. And now we are going to convert this to a matrix. Our matrix, M, needs to have 1,682 columns. Now let's get the size of that matrix M. As you can see, it's going to have 943 columns and 1,682 rows. Now I'm not going to print out the entire data set because it is very large. And every time I do print it out, it locks up my computer. So we're just going to keep it inside these variables, and you're just going to have to trust me that the data is there. Let's go ahead and compute the covariance matrix of our data set. Conveniently, there is a call inside HMatrix that does this for us. It produces the mean of each of our columns and the covariance matrix, and it's called mean covariance. And we just pass that in, and it produces the covariance matrix. So let's get the size of our covariance matrix. It is a much larger matrix, comparing each movie to each movie. That is going to be a square matrix of 1,682 values by 1,682 values. It is going to be a symmetric matrix, which we are going to use in the next video series for our eigendecomposition. So in our next video, we're going to do eigendecomposition. In this video, we will be performing the eigendecomposition process of our covariance matrix. So in this video, we're going to be performing eigendecomposition of our covariance dataset. We're going to be exploring the eigenvalues produced by this process, and then we're going to determine how to find a collection of eigenvectors for our next phase, which is dimensionality reduction. I'm back in my Jupyter Notebook. In our last video, we performed the covariance of our dataset, and we found the symmetrical covariance. What we need to do now is to perform the eigendecomposition process. Now there's a number of functions which perform eigendecomposition in Haskell, but we're going to use one in particular that allows us very fast eigendecomposition if we have a symmetric matrix, which as a result of covariance, we know that we do. The eigenvalue decomposition process always produces eigenvalues and eigenvectors. I'm going to name those e-vectors and e-values. And the function is called eigsh. We're going to pass in our covariance matrix. So even though we have a very large matrix, this process is actually quite fast. So let's look at the size of our e-vectors. We have 1,682 values by 1,682 values. Now this e-vectors matrix is a matrix of columns, and we're going to depend on each column for our future results. Now let's look at the e-values. We have 1,682 values. Now, as I mentioned in our first video in this section, the values themselves represent how interesting the data is. So if I get the sum of this list, I see that I have a total sum of 1,193. Now that number doesn't mean a whole lot, but just kind of keep that number in mind. Let's look at the first value in our list. So I'm going to take the sum and I'm going to take 1 from our list. Now the first eigenvalue in our list is 201. Now you recall that the sum of our list is 1,193, and so you can see that most of the interesting data is in that very first vector. And what I can do is I can take this list and I can expand this out to 2, and I can see that just by adding the second column I can get 258. Now our goal here is to make this number as large as possible while making this number here as small as possible. Now if I make this as large as possible, that's 1,682, I get my full sum. Now, one of the nice features of the Eig-SH process is that all of the eigenvectors and eigenvalues are going to be sorted for you, where the largest eigenvalue is going to be the first and the smallest eigenvalue is going to be last. So we can just simply use the take feature and start collecting our largest eigenvalues. So if I kick this up to about 50, you can see that I'm over halfway to my goal of hitting 1,193. And if I take this up to about 100, I've hit into the 700s. So this is a give and take. The larger that you make this number, the more data you'll be forced to work with and dig through later on. Whereas the smaller you make this number, the less accurate your results will be. And this in general is the give and take behind principal component analysis. We want to make this number large enough, but not too large. Kick this up to 200, you'll see we hit close to 1,000. Now 200 is still a long ways off from our original size of 1,682. So I'm going to stop at 200, and we're going to pick back up here in the next video. So in our next video, we are going to use our magic number of 200, and we're going to perform dimensionality reduction. In this video, we will finally be reducing our original data set to something smaller. So in this video, we're going to be extracting a submatrix from our covariance matrix based on the values that we learned about from our last video. We're going to be using that extracted submatrix in order to perform dimensionality reduction on our covariance matrix. And then we're going to be looking at some of the effects of that dimensionality reduction, as well as preparing ourselves for the next video on creating our recommendation engine. So I'm back in my Jupyter notebook. We decided on using 200 eigenvalues because that value is fairly close to our original 1,193. It's sort of the general weight of 200 eigenvalues is sufficient in order to say we're getting most of the data in our matrix with just 200 columns. So first we need to extract our submatrix based on these 200 columns. I'm going to call this extracted submatrix R. So if I look at size R, it's going to represent the first 200 columns. It's still going to have 1,682 rows, but only 200 columns. Using this, I can reduce the size of my original data set. I'm going to call this M prime. And to do that, I simply multiply M times my reduced data set, and that produces M prime. Let's look at the size of M prime. You can see it's 943 rows, which represent my 943 users, but there's only 200 columns. So this reduced data set still has most of the information we need in order to produce recommendations. Now, I would like to introduce you to a person who we will name 11. We're going to do a query on 11. Now, in our data set, 11, we can see that 11 is 39 years old, 11 is female, and 11 has an occupation listed as simply other. We can also see where 11's zip code is in the United States. Let's look at 11's favorite movies. Right. Now, what this query is going to produce is it's going to produce a list of titles from our items table where 11 has rated those movies with a score of at least 4 out of 5. We can see 11's favorite movies. There's movies such as Ghost, 2001, A Space Odyssey, Psycho. Down here you can see the very last one, Star Trek 3, Search for Spock. One Flew Over the Cuckoo's Nest. It looks like 11 likes science fiction and likes horror. You can see E.T. the Extraterrestrial there. That's a great sci-fi movie. Now, what sort of movies might you recommend to 11? And those are the sort of things I'd like for you to think about as we go into our next video using our reduced data set, M prime. So, in our next video, we will create our recommendation engine. Remember our user 11 from our last video? Our 39-year-old woman who likes sci-fi and horror movies? Let's see if we can come up with a few movie recommendations for 11. So our goal in this video is to create a recommendation engine. We're going to prepare our user to be compared across all users. We're going to use a formula known as the Euclidean squared distance measure. I believe we've introduced it before in past videos in order to find users who are close to 11. We're going to evaluate 11 across all of our reduced users in the data set. We're then going to recommend some movies for 11. So let's get to it. So I'm back in my Jupyter Notebook. Let's begin by pulling 11 out of our data set. Now, because of how the user indices work, 11 is going to be found at index 10. So we're going to copy from rows. We're going to replicate 943 times user 11, which is going to be at index 10. And so we are replicating index 10 943 times, and then we're converting that into its own matrix, which is just going to be a copy of those rows. All right, let's look at the size of copy. And you can see it's the same size as our reduced matrix. Let's come up with the difference squared of this particular, of these two matrices. So that's going to subtract the two matrices and square all of the results. So this is part of the Euclidean squared distance measurement. What we need to do now is we need to sum up each of our rows and convert that to a list. So we'll name that diff list, and we will map, and we will sum up each row. To list. There we go. And we will do this from 0 to 942 times for our 942 users. Now let's look at the first few elements in diff list. I'm going to come up with the first 20 elements. So take 20 from diff list. If you recall, we took index 10 as our starting point, and so if you'll notice at position 10 where I have my mouse pointer, you'll see that it's 0.0, and that's as it should be. The person closest to 11 will be 11. but we're really looking for the second closest person to 11 in our data set. So let's begin that process. We're going to match up every different score in this list with its index position. So diff index, I'm going to zip up diff list with its index position. What we're going to do now is we're going to sort by the first element in this list. So I'm going to take the first 5 elements, we're going to sort by, and you have to pass in an ordering function. So if the first of A is less than the first of B, then we're going to say that's less than, else we're going to say that's greater than. We're going to pass in our diff index. And you're going to see here, these are just the first 5 elements. And so at index position 10, we get a score of 0, as we should expect, because the person closest to 11 is going to be herself. And we have the scores incrementing upward from there. So the person closest to 11 that's not herself is going to be at index position 186. So let's come up with some recommendations based on this particular user. So I'm going to create a quick function here that's called movie recommend. And it's going to take an I and an A and a B. And I is going to represent a movie index, whereas A and B are going to represent users. So at M, and M is going to represent our original matrix, M for user A and I, if that equals 0, and M for user B for the same movie, I, if it's at least 4, we're going to return that to be true. And now I'm going to create a recommendation list, which I'll call rec, where I'm going to map over all of our movies. We'll say for index position I, we're going to use our movie recommend quick function. And we'll say, does user 10 need the recommendation of this movie from user 186? And we'll pass over all of our 1,682 movies, 0 from 1,681. So that's going to be a list of Boolean values, a lot of trues and a lot of falses. So let's filter that list to just the values which are true. So filter, we'll say, based on first, of our zip of recs from 0 to 1. So we're going to zip up our recommendations, which are just a sequence of trues and falses. We're going to line that up with a sequence of integers, 1 continuing on to infinity. And we're going to filter out just the elements which are true. And so we see a list of movies listed here. These are movies which user 187 has liked with either a rating of 4 or 5, that we know that user 11 hasn't seen before, and because 187 is going to be the closest user to 11, hopefully these are movies that 11 will like. So let's look at the first movie here. It's a 23. So quick query db select title from items where items.movie ID is equal to 23. All right, we got taxi driver. Maybe 11 will like taxi driver. Let's look at another recommendation. Let's say 64. The Shawshank Redemption. Ah, that's a classic movie. Hopefully she'll like Shawshank Redemption. And then let's pick out one more. Let's do 65. What's Eating Gilbert Grape? All right. Those are good selections of movies, and hopefully 11 will appreciate them. All right. Let's end with our section review. So we began this section with an exploration of the math behind eigendecomposition and the algorithm for principal component analysis. We prepared our data set and found the covariance matrix of the prepared data set. We performed the eigendecomposition of our covariance matrix. And then we found how many eigenvectors we would like to pull from that covariance matrix. We reduced our original dataset based on the number of values discovered from our eigendecomposition of our covariance matrix. And then, using that reduced dataset, we found a user in our database, and we recommended a few movies to user 11. So, that is the conclusion of advanced Haskell data analysis. I hope you enjoyed this.